Hi everyone, welcome to goclasses. In this session, we will solve GATE previous year questions from the topic minimal DFA. In the previous lecture, we have already seen the concept of minimal DFA, how to minimize a DFA. Now, in this lecture, we will solve each and every GATE previous year question based on minimization of a DFA. Let's start with this question. This is GATE 2007 question. Consider the following finite state automaton. So this DFA is given to you. The minimum state automaton equivalent to the above FSA has the following number of states. Okay. So the question is asking how many states are there in the minimum DFA. Okay. So in the minimal DFA, so let's solve it. In this question, first of all, you can notice that this Q3, this is an unreachable state, so we can remove it, correct? Okay, I told you that the first step in the minimization, that is removing the unreachable state, because this Q3 is not reachable from the initial state. Initial state is Q0. From the initial state we cannot reach this state Q3, so we can remove this unreachable state, because if you remove the unreachable state, then remember the language will not change. Okay, so this is unreachable, we can remove it. Now what we have, now we have, remember, because we can remove this unreachable state, so I can remove this Q3. Okay, and these transitions are also gone from the Q3, all the transitions are also gone. So now this is the finite automata we have. Now this is the DFA that we have. In this DFA, tell me which states are equivalent. Let's find out which states are equivalent. You can see this is a non-final state and these two are final state. So I told you that final and non-final state, they are never equivalent. So I can say this Q0 is not equivalent to Q1. This Q0 is not equivalent to Q2. Okay, now let's check Q1, Q2. Are they equivalent? Tell me. Let's check Q1, Q2. Are they equivalent? You can easily see one thing, that this Q1, Q2 on every string, what they will do? They will go to final state. Yes or no? Okay, see, from this Q1 on any string W, whatever string W you take, remember you can take any string W you can take. Okay, so from this state Q1 on any string W, where you will go? We will go to a final state, either Q1 or Q2. Remember, we will go to a final state, we will go to. Similarly, from the state Q2 on any string W, we will go to final state. Yes or no? So you can notice that on any string W, Q1, Q2, both are always going to final state. So I can say that Q1, Q2, they are equivalent. Okay, they are equivalent because on every string, this Q1, Q2, they are going to final state, always they are going to final state. Okay, so that is the reason I can say that these two states, they are equivalent, so we can merge them. Okay, so that is the reason we can merge these two states, and when you merge, finally you will get two states. Yes or no? Okay, we are going to get two states, so the number of states in the minimal DFA, that will be, answer will be 2. Okay, very simple. Is this point clear? One more thing you can notice in this question, that once you remove this state Q3, because Q3 is unreachable state, after removing this state Q3, one thing that you can easily notice, that is, what is the language of this DFA? Tell me, what is the language of this DFA? Let's call it machine M. So what is the language of this machine M? You can easily see that is containing A. Yes or no? Language is strings containing A. Okay, strings containing A. Strings containing A. So for this language, you can directly create the minimal DFA. Yes or no? For this language, you can directly create the minimal DFA. The minimal DFA for containing A, that will be like this. Okay, if B's are coming, we will ignore. We are waiting for A. So when the A will come, then now we will go to final state, and whatever comes, we will accept. Yes or no? So you can easily see that we will get two states in the minimal DFA. Okay, this is another way to create minimal DFA from the language. Basically, what you do, you recognize what is the language accepted by this machine. So if you notice, the language is containing A. Yes or no? Because you can notice, if B's are coming, we will ignore. When A will come, then we will go to final state. Now you can see, now we will stay in the final state. See, when B's are coming, we are ignoring all the B's. Okay, when the first A will come, then we will go to final state, and then we will stay in the final state. Yes or no? Whatever comes, A comes, B comes, A comes, B comes, whatever comes, then we will stay in the final state. So I can say that the language is strings containing A. For this language, you can directly create the minimal DFA that will have two states. So the answer will be option B. Okay. Let's solve this GATE 2011 question. Definition of a language with alphabet A. Basically, we have this alphabet that has only one symbol. This is a unary alphabet, or you can say unary alphabet. Okay, so you can see definition of a language with alphabet A is given as following. L is set of these strings a power nk where k is greater than 0 and n is a positive integer constant. Remember what is n? See, k is greater than 0 means the value of k you can take, for example, you can take 1, you can take 2, you can take 3, you can take 4 and so on, because k is greater than 0. Okay, now you can see what is n. N is a positive integer constant. Okay, remember n is a constant, you have to take a constant value. Now the question is asking that for this language L, this is your language L which contains a power nk, these strings are there in this language L. What the minimum number of states in the DFA to recognize L? Now let's understand this language and then you can easily solve it. See, the language that is given to you, first of all the alphabet is only symbol A. We have this is the alphabet, only we have one symbol, that is A. Okay, now the language that is given to you, that is a power nk, where remember k is greater than 0 and remember n is a constant, this is a positive integer constant, n is a constant and remember n is a positive integer means n belongs to natural number, means n belongs to either 1 2 3, because 0 is not a positive number. Remember 0 is neither positive nor negative. Okay, so n is constant means n can be 1, n can be 2, n can be 3 and so on. Okay, but because it is a constant, so you have to take fixed value. Now let's assume that n is 2. Okay, let's assume n is 2, then what will happen? Now our language, if you take n equal to 2, then our language will be, this will be our language, yes or no, a power 2k, where k greater than 0. Okay, k is greater than 0, so I can say that if you put k equal to 1, then you will get double a. If you put k equal to 2, you will get a power 4. If you put k equal to 3, you will get a power 6, a power 8, a power 10 and so on. Yes or no? So you can easily see this is your language. Now for this language you can easily create the DFA. Remember here we are assuming n is 2. Okay, let's assume that n is 2, because n is a constant value, n is positive integer constant. Positive integer means 1 2 3 4 and so on. Okay, remember 0 is not a positive number, 0 is neither positive nor negative, 0 is neither positive nor negative. Okay, the positive numbers, the positive integers, what are the positive integers? Positive integers are 1 2 3 and so on. So these are the positive integers, and because n is a constant, so n is a fixed value. Okay, so let's assume that n is 2. If you assume n is 2, then this will be your language L, because k is greater than 0, so you can put k equal to 1 2 3 and so on. Now for this language, can you create the minimal DFA? Can you create the minimal DFA for this language? Very easily you can create the minimal DFA. Remember the alphabet is only one symbol, that is A. Okay, so you can see that what we want to accept, we want to accept a power even. Okay, but we don't want to accept the empty string. So remember what we want to accept, we don't want to accept the empty string, we want to accept a power even. So a we will ignore. Then if another a comes, now remember what we will do, we will go to a final state, yes or no. Okay, double a is accepted. Now what we want, now we want to accept a power 4. So what we will do, now we want to accept a power 4, then what we will do, tell me. So here you can notice that we have accepted double a, I want to accept a power 4, so I can make this transition a. Now you can easily see what I am accepting. Notice I am accepting double a, then a. Okay, so now this is the DFA, yes or no. Now you can notice we are accepting double a power 4, a power 6, a power 8, a power 10 and so on. So you can easily see this is your minimal DFA. Okay, is this clear? This is the minimal DFA. Let's call it q0, let's call it q1, let's call it q2. So the minimal DFA has how many states? If n is 2, if you make n is 2, then the answer must be what? Then the answer must be 3. Yes or no? If you make n equal to 2, then the answer must be 3. Remember, this is a minimal DFA. You can easily see. Okay, because all these states, they are distinguishable. They are not equivalent. Okay, you can easily see this is the final state. So final state, non-final state, they are never equivalent. Okay, now let's check these two non-final state. Are they equivalent? No, they are not equivalent. Okay, they are distinguishable by A. You can see this state on A going to final state, this state on A going to non-final state. So you can see this is a minimal DFA. Okay, so very easy. You can see if the n value is 2, then answer must be 3. So tell me which option is gone. Remember, if you assume n equal to 2, then it simply means answer must be 3. So put n equal to 2, then answer must be 3. So this option is gone. Okay, so you can see the answer depends. Okay, so here you can easily see the answer does not depend on k. Okay, the answer will be option B. Yes or no? But this is not a complete analysis, but I hope you understood this. Okay, remember, if you take n equal to 3, then what will happen? If you take n equal to 3, let's assume n is 3, because n is constant. So let's assume n is 3. Now what will be the language? K is greater than 0. So the language will be a power 3 if you put k equal to 1, a power 3 if you put k equal to 2, a power 6 if you put k equal to 3, a power 9, a power 12, and so on. This is the language. Now for this language, can you create the minimal DFA? Let's create minimal DFA for this language. That will be like this. Okay, from the initial state, remember, we want to accept a power 3. Okay, so a comes, another a comes, another a comes. This we want to accept. We want to accept a power 3. Remember, the alphabet is single symbol, that is your symbol a. Okay, so now you can notice this a power 3 is accepted. Now we want to accept 3 more a's. Yes or no? 3 more a's we want to accept. Remember, so should I do this? Please tell me, should I do this? Let me know. Should I do this transition? Should I make this transition? Because I want 3 more a's. After 3 a's, remember, I have accepted 3 a's. I have accepted 3 a's. I want to accept 3 more a's. 3 more a's should come. So if I do this, then what is happening? Then 4 a's are coming. Okay, so remember, if I make this transition, then remember, this a and these 3, so 4 a's are coming. So what should I do? I should make transition to this state, so that this a and these 2 a's, so 3 a's can come. Yes or no? Notice, 3 a's, then 3 more a's, then 3 more a's, 3 more, 3 more, 3 more, like this. Okay, is this clear? So this is the point. So remember, the arrow will go to this state. Okay, now you can notice this is a minimal DFA. Let's call it Q0, Q1, Q2, Q3. Okay, this is a minimal DFA. So you can easily see, if n equal to 3, then the answer is what? Then the answer is 4. Correct? Yes or no? Minimal DFA will have 4 states. So you can easily see that answer will be option B. Now let's see the general case. Let's see the general case. So take n, means take n is your constant. Okay, n can be anything. Remember, n is your constant. N is constant value, that is greater than 0, constant. And also remember, n is greater than 0 because n is constant, positive integer. Okay, so here remember, your language L, what is that? That is like this, because k is greater than 0. So remember, your language is a power n, a power 2n, a power 3n, a power 4n. I am taking the general case. Okay, I am not taking any value of n, I am taking a general case. This is the language. Is this clear? I am taking a general case where I am not taking any specific value of a, any specific value of n I am not taking. So the language will be a power n, a power 2n, a power 3n, a power 4n, because k is greater than 0. So if I put k equal to 1, it will be a power n. If I put k equal to 2, it will be a power 2n. If I put k equal to 3, it will be a power 3n. So this is the language I will get. Okay. Now something interesting about this language, because your language is a power n. Okay, n is, then 2n is, then 3n is, then 4n is. So like this. Okay, it is like this. Remember, your string looks like this. Any string in W, that is like this. String in W, sorry, string in L. Okay, that will look like this. That it will be something that there will be n A's, there will be n A's, then there will be n more A's, then there will be n more A's. Okay, and so on. Yes or no? Is this clear? You can notice, n is, a power 2n means there are 2n a's, a power 3n means there are 3n a's. Okay, so this is the string in L look like. Okay, now you can easily see, first we want to accept a power n. Do you agree? We want to accept a power n. This is what we want to accept. Okay, so this is the point. This is what we want to accept. So like this. Okay, so let me accept a power n. Tell me, to accept n a's, how many states I need? See, to accept 1a, I need 2 states. To accept 2a's, I need 3 states. Okay, so like this. To accept 3a's, I need 4 states. So like this and so on. Finally, I can say that I will have total n plus 1 states, yes or no? Okay, so there will be total n plus 1 states, because remember, okay, if I call it q0, then for 1a it will be q1, okay, for 2a it will be q2, it will be q3, and so on, remember. So it will be here qn. Remember, from 0 to n there are n plus 1 states. Okay, is this clear? From 0, counting is starting from 0, because counting is starting from 0. 0 to n there are n plus 1 states. So now I have n plus 1 states. Now I have accepted this. Okay, this I have accepted. Remember, a power n I have accepted. Now what I need? I need more n, n more is, yes or no? After accepting n is, this string is accepted. Now I want to accept n more is, yes or no? N more is can come. So tell me, should I make this transition? If I want n more is, I want n is, n more is I want, then should I make this transition? No, because remember, here you already have n a's. So including this, basically you are having n plus 1 extra a's. But we want only n extra a's. Yes or no? We want only n extra a symbols. So that is the reason, remember, we should make transition here. Do you agree? Okay, because now this a and these are the n minus 1 a's. So total I will have n a's. Okay, is this clear? So it's like this. Okay, initially n a's, then n more a, then n more a, then n more a, and so on. Okay, so and this will be your final state. This last state, this will be your final state. So finally the answer is what? So tell me, minimal DFA has how many states? Minimal DFA will have how many states? That will be n plus 1 states. Okay, I hope this point is clear. Please tell me. So this is the complete analysis of this question. The general case, did you like? I personally like the general case, because the general case is telling you how to make DFA. You can see a power n, a power 2n means n a, 2n a, 3n a, 4n a, and so on. Okay, so the strings in L, they look like this: n a, then n more a, then n more a, and so on. Okay, so what you can do first, you can accept n a, then you need n more a. So this transition from the final state, it will go to this state. Okay, remember, it will go to this state, it will go to. So very simple. So finally your answer will be n plus 1. This is a nice question, beautiful question in GATE 2011. Now let's move on. Let's solve GATE 2011 question. A deterministic finite automata DFA with alphabet AB is given below. So this DFA is given to you. The alphabet is binary alphabet AB. Okay. Which of the following finite machines is valid minimal DFA which accepts the same language? Basically, the question is asking that you minimize this and you find a minimal DFA. Okay. For the same language, you have to keep the same language. Basically, we have to find the minimal DFA, nothing else. So this question is all about minimal DFA. We have to minimize the given DFA. Okay, the question is asking that these are the options. Remember, options are option A, B, C, D. Basically, question is asking which of them is minimal DFA. Okay, we have to keep the same language. You cannot change the language, of course. Okay, so let's find the minimal DFA. Let me tell you that there are many ways. There are many different ways to solve this question. The first, the first option is basically the first method is option elimination. Okay, actually in this question, these are the options given to you. And in these options, one thing you can easily notice, that is, see, this given DFA, is it accepting string B? Tell me, this given DFA, look at this given DFA. Is it accepting string B? What about string B? I'm asking this string B. So this string B is rejected by this given DFA. Yes or no? This string B is rejected. Correct? Okay. String B that is rejected by this given DFA. So string B should be rejected. And these are the options. Tell me which option is rejecting string B. You can see that this is accepting this DFA is accepting, this is accepting B. Correct? Okay. And you can see this is also accepting B. This is also accepting B. Also remember, this is also accepting B, correct? This is also accepting B. Okay, so all these options are gone. Remember, this option gone, this option gone, this option gone. So because three options are gone, so definitely this must be the answer. Yes or no? So this is method number one. Is this clear? This is method number one, that basically you can easily see that string B is rejected by the given DFA. Okay, the given DFA D, this is rejecting string B, but these three options, they are accepting string B. So automatically these three options are eliminated. Only one option is remaining. So this must be correct. Okay, this is method number one. What is method number two? Tell me what is method number two? That is minimization. Let's minimize because minimal DFA is unique. You already know that minimal DFA is unique for any regular language. Minimal DFA that is unique. Okay, so what you can do? You can simply minimize this and then you can check the options. Okay, let's minimize this. Okay, for the minimization, tell me which states you will check. Will you check Q comma T? Will you check the equivalence of these states Q comma T? No, because this is non-final, this is final. And I told you that final and non-final state, they are never equivalent. Okay, so we will check these states are equivalent or not. We will check these states are equivalent or not. Okay, so you tell me state S comma T, are they equivalent? Let me know state S comma T, are they equivalent? Are they equivalent? Yes, they are equivalent because remember, from these states S comma T, whatever string comes, okay, on any string, what will happen? On any string, they are where are they going? They are going to final state. Yes or no? Remember, this state S, on every string it is going to final state. This state T, on every string it is going to final state. So remember, S comma T, on every string they are always going to final state. So they are equivalent. Yes or no? S is equivalent to T. Very simple. This method we have already seen for minimization of DFA. Okay, the link I will provide you in the description. You can check it out. Basically, this is the most efficient method to minimize the DFA. You find, are they equivalent? These non-final these final states, are they equivalent? Also, these non-final states, are they equivalent? Okay, you don't have to apply the Hopcroft partition algorithm. If you apply the partition algorithm, that is time taking. Okay, that is time consuming method. But this is a very easy method. Okay, you can check the equivalence of S comma T. You can see that this state S comma T, on every string they are always going to final state, so they are equivalent. Okay, now what about these states P Q R? Let me know. What about P comma Q? You tell me about P comma Q. Let me know about P comma Q. Are they equivalent or not? State P comma Q, are they equivalent or not? Tell me. So they are not equivalent. They are distinguishable by whom? They are not equivalent. They are distinguishable by whom? You can see they are distinguishable by B, or I can say they are distinguishable by BA. Okay, on this string BA, what will happen? On this string, remember, this state P, on BA, this state P will go to final state, and this state, this Q will go to non-final state. Yes or no? So you can notice that P, Q, they are not equivalent. State P comma Q, they are not equivalent. They are distinguishable by whom? They are distinguishable by string BA. Okay, so they are not equivalent. What about PR? Tell me, what about PR? Let me know about PR. So they are also not equivalent. Why? What is the reason? You can easily see this P comma R on string A. This P is going to final, R is going to non-final. So they are also not equivalent. What about QR? Tell me what about QR? They are also not equivalent. QR is also not equivalent. Why? What is the reason? Because you can see that on symbol A, Q is going to final, R is going to non-final. So they are also not equivalent. So finally, the minimal DFA will have how many states? Remember, these states you can merge. The only thing is you can merge these states because remember, this PQR, they are distinguishable. Okay, this PQR, they are distinguishable. You cannot merge them. They are not equivalent. Okay, so you can see they are not equivalent. PQR, they are not equivalent. But remember, S is equivalent to T. So you can merge these two. S comma T, these states you can merge. So finally, the minimal DFA will have 4 states. Okay, there will be total 4 states will be there. One final state will be there. So let's check the options. You can see 3 states. This option is gone. This is three states. This is three states. This option is gone. Yes or no? Here you have three states. Here also you have three states. So these options are gone. You can see here you have two final states. This option is also gone. Okay, here you have two final states. So this option is also gone. You can see the answer will be this. You can notice we have one final state. We are merging S comma T. Yes or no? This state is basically your state S T. Is this point clear? You can notice the final state S comma T we can merge, and this is the minimal DFA we will get. So the answer is option A. Is this point clear? Please tell me. So very simple. There is another method to solve this question. What is that? There is another method to solve this question, that is you recognize the language. Tell me what is the language of this DFA? What is the language recognized by DFA D? You can easily see. Starting with A. Either you are starting with A, yes or no. If you are starting with A, then it is accepted. Every string that is starting with A, that is accepted. Or starting with BA, that is also accepted. So I can say the language is starting with A or starting with BA. Okay, is this clear? So the language is starting with A or BA. Now you can easily see all these options. Okay, the language is starting with A or starting with BA. We want, this is what we want. We want starting with A or starting with B. Remember, the language of given DFA, that is starting with A or BA. Starting with A or BA. Okay, so you can easily see that this option, this is gone. Okay, this option starting with A or BA, this option is also gone because this is final state. Okay, so B is accepted. Next, starting with A or BA, but here B is accepted, so this option is also gone. And finally, this will be your answer. You can notice starting with A accepted or starting with BA accepted. Okay, so finally this is your correct answer. Okay, so like this you can solve this question by many different methods. Whichever you like you can apply. Okay, but the best method is what you can do. You can simply minimize this DFA because minimal DFA is unique. So you can minimize this DFA. You can see that these states are equivalent, these states are not equivalent. Okay, so your minimal DFA will have 4 states and there will be one final state. So easily you can see that only one option is matching for this question. Now let's move on. Let's solve this GATE 2017 question. The minimum possible number of states of a deterministic finite automaton that accepts the regular language. This language is given to you and the question is asking that what are the number of states in the minimal DFA. The question is asking the minimum number of states. Remember, the minimum possible number of states in a DFA. So the question is asking minimal DFA. Is this clear? Okay, in this question, we need to create minimal DFA for language L. This is what we need to create. I told you that minimal DFA for any language that is unique. Okay, so you will get a unique minimal DFA for this language L. Let's create. So the language, first you understand the language. The language is given to you like this, that we have W1, there is A, then W2. Okay, you can see W1, A, W2. These strings we have. These strings we have in the language where W1, W2, these are strings. Okay, remember W1, W2, they belong to AB whole star, means they are strings. They belong to AB whole star. AB whole star means strings of AB. Okay, AB whole star, what that means? This is sigma star. AB whole star means sigma star, that you already know. Okay, what is this AB whole star? This is same as sigma star. Sigma star is set of all strings. In this you have set of all strings. Okay, so remember W1 belongs to sigma star. What this means? What this means? This means W1 is a string of AB. Yes or no? W1 is a string of A comma B. So remember W1 is a string and W2 is also a string. This is what this statement means. Okay, because AB whole star is same as sigma star. Sigma star is set of all strings. So W1 belongs to sigma star means W1 is a string over A comma B. Okay, very simple. Now the question is saying that W1 length is 2 and W2 length is greater than equal to 3. Okay, these conditions are given to you that W1 length is strictly 2, exactly 2, and W2 length that is greater than equal to 3. Okay, first you understand this language, then you can solve this question easily. Okay, let's understand this language first. Remember, W1 has two symbols, because remember length of W1 that is 2. Okay, and remember W1 is a string, so W1 is a string of length 2. Do you agree? W1 is a string of length 2. You know that W1, this is a string. This is a string. From here you can easily see that this is a string. Okay, W1 is a string of length 2. Okay, so what is W1? What are the possibilities for W1? W1 is like this. Either W1 is AA or AB or BA or BB. These are the possibilities for W1. Okay, very simple. Now you can see what is your language. And remember W2, what is that? That is also a string. That is also a string of length at least 3. Okay, of length at least 3. So remember, it will be like this. See, your language, you understand the language. The language is like this, that this symbol can be A or B, this symbol can be A or B. Okay, remember, this can be A or B, this can be A or B. Then the third symbol must be A. Do you agree? Basically, this has length 2. Okay, then third symbol must be A. This must be the third symbol. Do you agree? The third symbol must be A. This must be the third symbol. And after that, W2 means a string of length at least 3, means after that you must have at least 3 symbols, because W2 has length at least 3. So remember, after this third symbol, you must have at least 3 symbols. Okay, they can be A or B, remember. They can be A or B. They can be A or B. They can be A or B. Okay, and remember, now whatever comes you will accept. So this is the minimum string. Minimum length string will be this much. Okay, minimum length string will be 6. And remember, after that you can have anything. Okay, here you can have anything. Here you can put any string. Here you can put any string belonging to sigma star. Okay, either you can stop or you can take A's or B's, whatever, anything can come. Okay, so this is the idea, because remember the length of W2 is at least 3. Okay, at least 3 means at least 3 symbols must be there. There can be more. There can be more symbols. So this is the idea. Now, once you understood this idea, you can easily create the DFA. Okay, so the DFA will be like this. The DFA will be that this is the initial state. In the initial state, remember, the third symbol must be A. Okay, remember the first symbol can be A or B. The first symbol can be A or B. In the initial state, this is the initial state. Let me call it Q1. In the initial state, either A can come or B can come. I don't care. Okay, either A can come or B can come. I don't care. Means the first symbol can be A or B. Okay, remember the second symbol can be A or B. Now, the third symbol must be A. The third symbol must be A. Okay, third symbol must be A. Now, three more symbols at least should come. Now, three more symbols should come. At least three more symbols should come. Remember, now either A or B should come. Okay, so one more symbol should come. Then one more symbol should come. Then one more symbol should come. Okay, now anything can come. Now anything can come. Now A, B, anything can come. Okay, this is the idea. Now you can easily notice that this is not a DFA, because in this state, if B comes, then what will happen? See, this is not a DFA, because what will happen if in this state Q3, if symbol B comes, then you can notice if the third symbol is B, then there is no chance of acceptance. Okay, if third symbol is B, you can easily see that if the third symbol is B, in this state, if symbol B comes, then what will happen? In this state, if symbol B comes, then there is no chance of acceptance, because remember, third symbol must be A. This third symbol must be A. This must be the third symbol. Okay, so if the third symbol is B, then there is no chance of acceptance, hopeless situation. There is no way you can accept the string. Okay, so we will go to a dead state. So this is the idea. So finally, how many states we have? You can see 4, 3, 7, and 8. Total 8 states we have. Yes or no? You can easily see 1, 4, 3. So that is total 8 states. So finally, I can say that the minimal DFA will have 8 states. Okay. Is this point clear? Sorry, this state will not be the final state. The final state will be this last state. Okay. The last state, this will be the final state. This will basically, this will not be the final state here. Okay. So this will be your final state. There will be only one final state in the minimal DFA. This is your minimal DFA. Let me tell you. This is your minimal DFA. Okay. And in this minimal DFA, you can easily see this is the only final state. There is only one final state in this minimal DFA. So total we have 8 states. So the answer will be 8. Is this point clear? So this is a nice question. You have to just understand the language L. Just understand what is the language L, what strings belong to the language L. Just understand this, and then you can easily solve it. The answer will be 8. Let's solve this GATE 2023 question. Consider the language over alphabet 0, 1. So alphabet is binary alphabet. This is the language given. W is a string on 0, 1. W belongs to 0, 1 whole star means W is a string over symbol 0, 1. W does not contain 3 or more consecutive ones. The minimum number of states in the DFA accepting the language L. Okay. So this is a very simple question. What we can do? First, we can create minimal DFA for strings containing 3 ones. See, what are the language? The language is simply saying that we should not have 3 or more consecutive ones. Yes or no? We should not have not containing 3 consecutive ones. Okay. Remember, this is redundant or more. This word is redundant, right? Tell me why. This is redundant. This is unnecessary. Tell me what is the reason? Because if you don't have 3 ones, then you cannot have 4 ones. Yes or no? If you don't have 3 consecutive ones, if you do not contain triple one, then you cannot have 4, 1, 5, 1. Yes or no? If you do not contain triple one, then you cannot contain 4, 1, consecutively 4, 1, okay, consecutively 5, 1, and so on. So this is the idea. So remember, this or more, this is just redundant. Okay, this word or more, this word is redundant. Okay, so not containing triple one. Let's create. So our language, what is that? That is not containing triple one. Not containing triple one. So what I will do, let me tell you. First, I will create the DFA for containing triple one. Okay, this is what I will do. Okay, first I will create for this language, I will create the DFA. And then what I will do? Then I will create the DFA for complement of L1. Okay, the question is asking what is L? L is complement of L1. Okay, the question is asking about L. So let me create the DFA for L1 first. Minimal DFA for L1 I will create. Okay, so you can easily see. I want L1 is containing triple one. I want triple one. Okay, in the initial state, I am waiting for triple one. Okay, so if 0 is coming, I will ignore. Okay, because I am waiting for triple one. If 1 is coming, I will be happy that I have seen 1. Okay, I am waiting for another 2 ones. If another one comes, I will be very happy. I've seen 2 ones. I am waiting for another one. If another one comes, I will be very happy that I have seen triple one. I have seen triple one. Now whatever comes, now 0 comes, 1 comes, whatever comes, I will accept because I want triple one consecutively. Okay, so once I get triple one, then I will be very happy. Whatever comes, 0, 1, whatever comes, I will keep accepting. Okay, but this is not a DFA. This state is done because in this state, on every alphabet symbol, we have created the transition. In this state, what will happen if the symbol 0 comes? You can see in this state, we have already seen 1. Now, if 0 symbol comes, we are waiting for double one. In this state, you can see we have already seen 1. We are waiting for double one. If symbol 0 comes, then what I want? I want triple one consecutively. So I have to wait for triple one. Yes or no? Again, I will wait for triple one. So very simple. In this state, if symbol 0 comes, then the progress is gone. Whole progress is gone. Whole progress is gone. I have to wait for another triple one because whole progress is gone. Similarly, in this state, after 1, 1, if 0 comes, then the whole progress is gone because I want consecutive 3 ones. I want consecutive 3 ones. So in this state, if 0 comes, the whole progress is gone. I will wait for triple one. Okay, so this is the DFA for containing triple one. Now, let's see for not containing triple one. This is your original language L. Your original language L, this is not containing triple one. So what I need to do? I just need to make the final state non-final and non-final final. Yes or no? This is what I need to do. I need to make this non-final final, non-final final. Okay, this will be final, and this final state I will make it non-final. This final state I will make it non-final. Okay, so this is the idea. Now this is the DFA. Let me tell you, this is the minimal DFA. Okay, let me tell you, this is the minimal DFA. Okay, and this is the minimal DFA for L, and the number of states are 4. There are 4 states. Okay, and one more interesting fact, let me tell you, we have already seen this in our lectures. This is that, see, if you have a DFA, if you have a DFA M for language L, okay, now in this DFA, if you complement the states, okay, if you complement states means you make final, non-final, non-final, final. Yes or no? In this DFA M, if you complement the states, what it means? Complement states means every final state you make it non-final, and every non-final state you make it final. Okay, so you complement the states, then you will get a new DFA. Yes or no? You will get a new DFA. Let me call it M complement. You will get a new DFA, this DFA. And remember, this new DFA will accept L complement. This new DFA will recognize L complement. Yes or no? So this is what we have done. First, we have created DFA for containing triple one. Then we have complemented the states. Then we will get DFA for not containing triple one. Yes or no? So this is the idea. Now let me tell you interesting point, that is, if this original DFA is minimal DFA, okay, means if you have this minimal DFA for L, minimal DFA for L, and if you complement the states, then remember the new DFA will be minimal DFA for L complement. Okay, so means if you have a minimal DFA for L and you complement the states, then you will get minimal DFA for L complement. If this original DFA is minimal, then the new DFA you will get, that will be also minimal for L complement. Okay, so this is what we have seen. What we did, remember, for containing, you can see, for containing triple one, we have created minimal DFA. Okay, this is the minimal DFA for L1. Okay, so we have created minimal DFA for L1. Now in this minimal DFA, if I complement the states, then I will get minimal DFA for L. Okay, if I complement the states, then remember I will get minimal DFA. This minimal DFA I will get for L. So answer will be 4 states. Okay, is this clear? So very easy, that answer will be 4 states. So the number of states in the minimal DFA for this language L, that will be 4. Okay. A student is asking, can you prove it? A student is asking, can we prove it that if you start from a minimal DFA and you complement the states, then you will get a minimal DFA for L complement? Can you prove it? Okay. A student is asking for the proof. What is the proof of this? So the proof I've already provided in our lectures. The link I will provide you in the description. Okay. So the proof, remember, the proof you can find, link I will provide in the description. Okay. For the proof, the link I will provide you in the description. So if you want the proof for this, actually this proof I have already covered. Okay. I will provide you the link in the description or in the pinned comment. You can check it out. Is this clear? Okay. So this is a very interesting point. Actually, there is a gate question on this point. Okay, in the gate exam already a question has come on this point, that if you have a minimal DFA for L and you complement the states, then you will get a new DFA. Remember, this new DFA will be minimal for L complement. On this point, there is a gate question also. Okay, and the proof I have provided in the description. You can find the link. Okay, you can find the link for the proof in the description. Also, you can find the link in the pinned comment. You can check it out. Okay. So watch it. Now let's move on. So we have seen this GATE 2023 question. The answer for this question will be 4. Now let's move on. Let's solve this GATE 2000 question. what can be said about a regular language L over unary alphabet A whose minimal finite state automata has two states? Okay, see, this is a very interesting question. What the question is asking, let me explain. The question is saying what can be said about a regular language L over alphabet A. There is only single symbol. Yes or no? There is only one symbol in the alphabet. We have only one symbol in the alphabet. Okay. Whose minimal minimal finite state automata has two states. Okay. So this is the question that, let me tell you one thing, that when the question is saying minimal finite state automata, actually, whenever the question is talking about minimal finite state automata, this is talking about minimal DFA. Okay, by default, whenever the question is saying minimal FA, minimal finite automata, then let me tell you, this is talking about minimal DFA. Okay, by default, minimal FA simply means minimal DFA. Let me tell you. Okay, is this point clear? So minimal finite automata, by default, it means minimal DFA. It does not mean minimal NFA. No. Minimal finite automata, by default, it means minimal DFA. It is given in the Ullmann book. Okay, also in many standard resources, this is given that by default, finite automata simply means DFA. So by default, minimal FA means minimal DFA. It does not mean minimal NFA. Okay. So anyway, let's see this question. The question is saying that you have minimal DFA of two states. Then what can you say about the language? The language must be this, the language must be this, the language must be this. Okay, so what can you say about the language? Let me tell you that all the options are actually wrong. Okay, see, first of all, the question is saying that you have a minimal DFA. You have a minimal DFA of two states. Okay, if I tell you that you have a minimal DFA, focus on this word minimal. Okay, if I tell you that you have a minimal DFA of two states, is it possible both states can be final? Tell me, my question is it possible both states can be final? Is it possible? If you have minimal DFA of two states, you have minimal DFA of two states, is it possible that both states can be final? No, it is not possible. Why? Because you have minimal DFA, so both are reachable. Do you agree? Because you have a minimal DFA, so all the states are reachable. Yes or no? So definitely every state is reachable because you have a minimal DFA. So definitely every state is reachable. There is no unreachable state because I am talking about minimal DFA. You have a minimal DFA with two states, then every state is reachable. Now you tell me, if both the states are final, then they will be equivalent. Do you agree? If both the states are final, then what will happen? Then they will be equivalent. Q1 will be equivalent to Q2. So then I can say it is not minimal. Okay, if both the states are final, then I can say it is not minimal. Why it is not minimal? Because if both the states are final, okay, then the language will be sigma star. Do you agree? Okay, if both the states are final, then if all the states are final, then the language will be sigma star. And for sigma star, what is the minimal DFA? For sigma star, the minimal DFA has how many states? The minimal DFA will have only one state. There will be only single state. So you can easily see the question is saying that you have a minimal DFA with two states. So is it possible that both the states can be final? The answer is no. Because remember, I'm talking about minimal DFA, so every state is reachable. Now, if both the states are final, then they will be equivalent. So you can merge these two. So basically, this is not minimal. That is the point. Okay, so both the states cannot be final. Now, the second point, is it possible both can be non-final? Is it possible that both can be non-final? Tell me. I'm asking, is it possible that both are non-final? That this state, first initial state is also non-final and this state is also non-final. Is it possible? Tell me. Again, it is not possible because both will be equivalent. If both are non-final and there is no unreachable state, every state is reachable, you can easily see that. Then if both are non-final, only two states you have, then they will be equivalent. So you can merge these two. So definitely this is not a minimal. This is not a minimal DFA. And also another logic. Let me tell you another logic. What are the language if both the states are non-final? If every state is non-final, then language will be empty language. For empty language, what is the minimal DFA? The minimal DFA will have how many states? There will be a one state, single state. So that is the reason I am saying that minimal DFA will with two states, both the states cannot be non-final, both the states cannot be final. So what is the conclusion? Give me the conclusion. Minimal DFA with two states, what is the conclusion? The conclusion is one must be final, another must be non-final. And remember, both must be reachable. Both must be reachable. You cannot have unreachable state in the minimal DFA. In the minimal DFA, we cannot have unreachable state. Both must be reachable. And the conclusion is that both must one of them, one state must be final. One state must be final. Another okay, another state will be non-final. Another state must be non-final. Okay, so far you agree with me that one state must be final, another state must be non-final. This is the simple conclusion. Okay, so now we got that one state must be final, another state must be non-final. So what are the possibilities? Let's create. Let's create what are the possibilities. And remember your alphabet. What is your alphabet? Alphabet is unary alphabet, unary alphabet, basically only single symbol, one symbol we have in the alphabet, that is A. So one state must be final, another state must be non-final. Okay, so what are the possibilities? The possibilities are like this. For example, this can be final, this can be non-final. Okay, is it possible I can have self loop on A? Is it possible I can have self loop on A in the initial state? Can I have self loop on A? Is it possible? No, it is not possible, because if I have self loop, then this will become unreachable. Yes or no? Do you agree with me? If I put self loop on the initial state, then this will become unreachable. But in the minimal DFA, I cannot have unreachable state. Every state must be reachable. So remember, I cannot put self loop. Okay, I must do this. On A, I must go to this state. Okay, but remember, in this state, what I can do? In this state, either I can do this or I can do this. Do you agree? Do you agree with me? Yes or no? Either I can put a self loop on A or I can do this. So tell me, here what is the language? In this situation, let's call it M1. Okay, tell me what is the language of M1? Only empty string is accepted. Yes or no? So this language is possible. Do you agree? This language is possible. Only empty string is accepted. So this is what I'm saying that, okay, read this question. You have minimal DFA with two states. Okay. Okay. So this is your alphabet. So that is the reason. Remember, what are the possible? This language is possible or not? This language is possible. Do you agree? This is a possible language. Okay. I am asking what is the possible language? So this language is definitely possible. Okay. What else is possible? Can anyone tell me? So you can see this language is possible. Set containing empty string. Only empty string is accepted. This is possible. Another possibility, what is that? What is the language of M2? Tell me the language of M2. That is even number of A's. Yes or no? A power even. Even number of A's. So this is another possible language. So remember, there is another possible language, that is A power even. That is A power even. So this is another possible language. Is there any other possible language? Do we have any other possible language? See, what I can do, I can make it final and I can keep it non-final. Okay, so remember, now I have M3. It will be like this. On A, I can go here. I cannot make self loop in the initial state, because if I make self loop in the initial state, then this will become unreachable. So that is the reason in the initial state, I cannot put self loop. Okay, I have to do this. Now there are two choices. Either I can put self loop here, or okay, or what I can do, or I can put this here. So only these are the possibilities. So tell me, what is the language of M3? The language of M3, what is that? That is A plus. Yes or no? That is like A plus. It is like A plus. I can say that language is A plus. Do you agree? A plus means basically it is like A power n, where n is greater than 1. N is greater than 0. n is greater than 0. Okay, so this is the idea. I hope all these points are clear. So remember, this is another possible language. Okay, let me write it, that this is another possible language, M3, that is A plus. That is A plus. Okay, so A plus is possible. Is there any other language possible? What is language of M4? That is odd number of A's. Yes or no? That is odd number of A's. A power odd. Okay, so this is another possible language. That is another possible language is A power odd. Okay, so remember, these are the possible languages. So actually in this question, let me tell you, okay, there are four possible languages. There are four possible languages. Is this clear? We have total four possible languages. Now, which option is correct? Tell me. The first option is saying L must be A power odd. Okay, focus on must be. L must be A power odd. This is wrong. L must be A power even. This is wrong. L must be A plus. Sorry, A star. This is wrong. Okay, is this clear? What about this one? L must be this or this. See, L must be this or L must be this. This is also wrong. Is this point clear? Please tell me. So remember, there is no option correct. None of the options is correct. So the final answer will be these are the four possible languages. Okay. This language only empty string is accepted, or A power even, or A plus, or A power odd. So there are four possible languages. Let me tell you. So in this question, no option is correct. Is this point clear? Please tell me. None of the option is correct. Okay. Let's move on now. Let's solve this GATE 2018 question. Given a language L, define L power I. See, you have a language L, then the question is defining L power I. That is L power 0 is set containing empty string. That we already know. This is standard definition. L power 0. L power I is like this. That is L power I minus 1 concatenate with L for I greater than 0. So this is just the definition of L power I. That is standard definition. Okay, yes or no? So you can easily see. So this is a standard definition, nothing else here. Because we already know, you already know that L power 0. See, from the basic concepts, you already know that any language you take any language L, what I can say, for any language L, what will happen? We already know that L power 0, that always will be set containing empty string. Okay. And remember, what will be L power n? That will be like this. That will be L power n minus 1 dot L. Okay. Yes or no? So this is the simple point. Very simple point. Now, this same thing is given here. The definition of L power I. This is the standard definition, nothing else. Okay. So this is a standard thing. This is the standard definition. Okay. Now the question is saying the order of a language L is defined. Remember, they are defining a new concept. Let me tell you, this order of language, this is not a standard concept. This is not a basic concept. They are defining in this question, they are defining a new concept, a new terminology. They are defining in this question, the definition they are giving you. Okay, so remember, this is not a standard concept, order of a language. This is not a standard concept. In this particular question, they are defining a new terminology and they are also giving you the definition. They are saying order of a language is the smallest k such that L power k equal to L power k plus 1. Smallest k such that L power k equal to L power k plus 1. Now the question is saying that consider the language L1. Okay, this DFA, let's call it DFA M. Now the question is saying the language of this DFA, that is L1. Okay, the order of L1. The question is asking what is the order of L1. So let's solve it. First, you find what the language of this machine. See, this machine M is given to you. That is, you have final state. Initial state is final state. If 0 comes, then you go to final state. If another 0 comes, you go to non-final state. And If another 0 comes, you go to final state. So this is the DFA that is given to you. So tell me what is the language. The question is saying that LM, the language of this machine, that is L1. Okay, the language of this machine, that is L1. So tell me what is the language L1. You can see empty string is accepted because initial state is final. In the DFA, empty string is accepted if and only if initial state is final. Okay, this we have already seen in our lectures that in any DFA, this is the DFA, in any DFA, empty string is accepted if and only if initial state is final state. So empty string is accepted. You can easily see that string 0 is also accepted. You can see 0 is not accepted, but 000 is accepted. Okay, what the next string accepted? You can see 0. After 0, you can see that 0 power 4 can come, means total 0 power 5. I can say total 0 power 5 is accepted. 0 power 7 is accepted. 0 power 9 is accepted. 0 power 11 is accepted, and so on. Okay, is this point clear? So you can see that it is basically 0 power odd. See, the point is, what is the language L? This is a empty string, comma, 0 power odd. 0 power odd. Okay, this is your language L. Can I say? Because you can see 0 power 1, 0 power 3, 0 power 5, and so on. So this is your language. Okay, remember your language is empty string union 0 power odd. This is the language. Okay. Now the question is asking what is the order of L1. See, the question is asking what is the order of L1. What is the definition of order? Order means this is the smallest value such that L power k equal to L power k plus 1. Okay. So let's find out. Once we have this language, see, your language you have already have. This is empty string, then 0 power 1, 0 power 3, 0 power 5, 0 power 7, basically odd powers of 0. Okay, odd powers of 0, 0 power odd. So this is the idea. So tell me what is L power 0. Remember, we have to find, we have to find, this is L1. Okay, we have to find what is order of L1. And remember, the definition is like this. The smallest k, we have to find smallest k. Smallest k we have to find such that L1 power k is equal to L1 power k plus 1. Okay, is this clear? We have to find smallest k such that L1 power k is equal to L1 power k plus 1. So let's start with 0 because the question is asking smallest k. So let's start with k equal to 0. Okay, tell me what is this L1 power 0? Let me know. What is this L1 power 0? Can anyone tell me? That will be set containing empty string. Yes or no? This is set containing empty string. Tell me what is L1 power 1? That will be same as L1. Yes or no? That will be same as L1. Means empty string 0 power odd. Okay. What is L1 power 2? Tell me what is L1 power 2? Let me know. What is the power 2 of this language? L1 power 2 means L1 dot L1. Okay. So L1 dot L1 means empty string 0 power odd dot empty string 0 power odd. So tell me what will happen. Can I say you will get every string? See, you will get empty string. Notice one thing. You will get empty string because empty string, when you concatenate, this is the concatenation, then you will get empty string. Next, can you get 0? Yes. From here you can get 0 power odd. Notice, from here you can get all the 0 power odd. Do you agree? If you do empty string with this one, please focus that if you do this, then what it will give you? Then what it will give you? It will give you 0 power odd. So all the 0 power odd you can easily get. 0 power 1, 0 power 3, 0 power 5, everything you can get. Okay. Next, you can notice this 0 power odd with 0 power odd, what it will give you? 0 power odd with 0 power odd, what it will give you? It will give you 0 power even also. Yes or no? So you will get all the 0 power even also. So basically you are getting every string. Can I say you are getting like 0 star? You are getting every string. Is this point clear? Let me know. Is this point clear? Please tell me. So remember, for your language L1, or let's call it L, no problem. Okay, basically L1, let's call it L. For simplicity, let's call it L. Your language was like this: empty string, 0 power odd. This was your language. Now we have found what is L power 0. That is set containing empty string. Okay, we have found what is L power 1. That is L itself. Okay, and we have found what is L power 2. L power 2, what is that? That is L dot L, and that is 0 star. Yes or no? You will have everything. You will have odd zeros, even zeros, everything you will have. Okay, odd 0, even 0, everything you will have. Now tell me, what will be L power? What will be L power 3? Tell me, can I say your order will be 1? So far, did you get L power k equal to L power k plus 1? Tell me, so far, did you get L power k equal to L power k plus 1? So far, did you get? I'm asking, because remember, order of L, what is that? Focus. What is order of L? This is smallest k. This is smallest k such that L power k is equal to L power k plus 1. So far, did you get L power k equal to L power k plus 1? No. So we have to find what is L power 3 also. L power 3 means what is that? That is L square dot L. Yes or no? L power 3, that is L square dot L. L square, that is 0 star. Yes or no? L square, that is 0 star. That will be like this. Okay, that is empty string, 0, double 0, triple 0, everything. Okay, dot. What is L? L is 0 power odd. Okay, so tell me, what will be their concatenation? What will be L cube? You can notice L cube will have empty string. You can notice that. If you notice one thing, that all of them, with empty string, if you concatenate them with empty string, all of them, if you concatenate with empty string, you will get 0 star. You don't need this. There is no need for this. Okay, yes or no? You will get 0 star. So you are already getting 0 star. So remember, L cube is 0 star. So now did you get L power 2 is 0 star, L power 3 is 0 star? Yes or no? So what we got? Remember, we got that L power 2 is equal to L power 3. Both are same. Do you agree? Both are same. Both are equal to 0 star. Okay, so tell me what the order of L? Order of L will be 2. So the order of L will be 2. Why? Because this is the smallest value. Because this is the smallest value. This is the smallest such that L power 2 is equal to L power 2 plus 1. Okay. So remember, the value of k will be 2. So order will be 2. Is this point clear? Order of L will be 2. Please tell me. So very simple point. The question is very simple. The question is asking what the order of the language of this machine. That will be 2. Okay. Because from here you can find what is L1, and then you can see that L1 power 2 is equal to L1 power 3. Okay. So this will be the order. This will be the order, because order is smallest case such that L power k equal to L power k plus 1. Okay, so this is a nice question. In this question, a new thing is defined. Please notice, they have defined a new terminology. They have given you the definition. Your task is to analyze this. You understand the definition and then you do the analysis. So this question is purely based on analysis. Okay, the new terminology, the new concept is defined. This is not a standard concept. This is a new thing that is defined in this question. You just understand this. Okay, and then you analyze this and then you get your answer. Answer will be option. Answer will be 2. Okay. And remember, don't say that answer will be 3. See, some students, they can do this. For example, you can see L1 power 2 equal to L1 power 3. Some students, what they can do, they can put answer equal to 3. But this is wrong, because the question is saying that order of L is smallest case such that L power k equal to L power k plus 1. Okay, means L power k is equal to L power k plus 1. So order will be this. Order will be 2. Okay, let's move on now. Let's solve this GATE 2015 question. The number of states in the minimal DFA corresponding to the regular expression 0 plus 1 whole star followed by 1 0. So basically, what is the language? The language is ending with 10. Yes or no? See the language. Look at the language. For this language L, the regular expression is given to you that is like this: 0 or 1 whole star means sigma star, followed by 1 0 means ending with 1 0. Yes or no? Okay, remember this simply means that the strings are ending with 1 0. Okay, here anything can come. This 0 plus 1 whole star, this simply means sigma star. Okay, this simply means this is same as sigma star. So anything can come, but at the end 1 0 should come, ending with 1 0. This is the language that is given to you. Okay, for this language, let's create the minimal DFA. Remember, our language is ending with 1 0. Ending with 1 0. Alphabet is 0 comma 1. This is the alphabet. Okay, so let's solve it. Ending with 1 0. So very easily you can create the minimal DFA. Let me create the minimal DFA directly. We have created minimal DFA from the languages directly. Okay, what you can do? See, in the initial state, I'm waiting for what? I want to end with 1 0. Remember, I want to end with 1 0. So I'm waiting for 1 0. Okay, so tell me, when I will trigger, see, in the string, if zeros are coming, I don't care because I'm waiting for 1 0. I will trigger when the 1 will come. Yes or no? So if zeros are coming, I will not trigger because I'm waiting for 1 0. I want to end with 1 0. So if zeros are coming, I will not trigger. When 1 will come, I will trigger. When 1 will come, I will trigger. Yes or no? I will trigger. Now I have seen 1. Now I'm waiting for 0. Okay. Now, if another 0 comes, then I will think that I've ended with 1 0. Yes or no? What I'm thinking, if another 0 comes, I'm thinking that I've ended with 1 0. I've ended with 1 0, right? Okay. Now you tell me, in this state, okay, see, focus on this state. In this state, I've already seen 1. I'm waiting for 0. If another 1 comes, let's assume if another ones are coming, then I'm still waiting for 0. Do you agree? Yes or no? So in this state, if 1 is coming, then self loop because I'm still waiting for 0. Do you agree? Because if ones are coming, no problem. I'm still waiting for 0. Okay, so that is the reason I can make a self loop here. What about this state? I am thinking that I've ended with 1 0. I want to end with 1 0. Now in this state, I am thinking that I've ended with 1 0. You tell me, in this state, if symbol 0 comes, I've ended with 1 0. If symbol 0 comes, then I need 1 0 again. So the whole progress is gone. Yes or no? In this state, if 0 comes, then the whole progress is gone. I have to again wait for 1 0. See, this state is saying, notice what this state is saying. This state is saying that you have already ended with 1 0. Now I'm saying if another 0 comes, now you have to wait for 1 0 to end. You have to wait to end. You have to wait for 1 0 to end. Okay, so basically the whole progress is gone. If another 0 comes, the whole progress is gone. You have to wait for 1 0. So you have to go to the initial state. In this state, if symbol 1 comes, then see, in this state, we have already ended with 1 0. Now, if symbol 1 comes, then I just wait for 0. Then I will just wait for 0, yes or no? So, very simple. In this state, if symbol 1 comes, then I will just wait for 0. So, this is the DFA. Is this clear? And you can see this will be your final state. This is the minimal DFA. You can easily see. Tell me why this is minimal DFA. Let me know, because you can easily see that these states, these are non-final state. They are distinguishable by whom? They are distinguishable by 0. This state on 0 going to non-final state, this state on 0 going to final state. So they are distinguishable. And I told you that final comma non-final state, they are never equivalent. So this is a minimal DFA. So the minimal DFA has how many states? Minimal DFA has 3 states. Okay, so very simple. The number of states in the minimal DFA, that will be, answer will be 3. Very simple question. In our lectures, we have already created DFA from the language directly. See, you don't have to create first NFA, then DFA, then minimize the DFA. You don't have to do that. If a language is given to you, you can directly create the minimal DFA. We have already done a lot of practice. Okay, I have full confidence on you that if a language is given, you can directly create the minimal DFA. Many students, what they do, From the language, first they will create the NFA, then they will convert into DFA, and then they will minimize. This is what many students do, let me tell you. But this is a dumb method. You should not do this. This is dumb. Okay, what you can do from the language, with analysis, with practice, you can directly create the minimal DFA. We have done in our lectures. Let's solve GATE 2021 question. The language L, which is subset of sigma star, here sigma is 0, 1. You know that every language is subset of sigma star. So this is given that L is a language. And the question is saying L is a regular language accepted by some minimal DFA with K states. Okay, the question is saying that what is L? L is a regular language. L is some regular language. We don't know which language. This is some regular language. And the question is saying that minimal DFA has K states. Minimal DFA for L has K states. We already know that minimal DFA for any language is unique. Do you agree? Minimal DFA for any regular language is unique. So the question is saying that minimal DFA for L that has K states, this is already given to you in the question. Now the question is saying which one of the following languages must necessarily which one of the following languages must necessarily be accepted by minimal DFA with K states? See, the question is beautiful. The question is saying if L has minimal DFA K states, if L has minimal DFA with K states, then which of the following necessarily will have minimal DFA with K states? Means if L has minimal DFA with K states, then which of these options will necessarily have minimal DFA with K states? So the answer is L complement. So the answer is L complement, that is option C. Yes or no? Notice I told you in our lectures that if you have a DFA, if you have any DFA, minimal or not, if you have any DFA, let's assume DFA M for language L, and in this DFA, if you complement the states, in this DFA, if I complement the states means what? It simply means that every final state, I make it non-final, and every non-final state, I make it final. Means in this DFA, for language L, remember this can be any DFA, minimal or non-minimal. So this can be any DFA for language L. If you complement the states in this DFA, then you will get a new DFA. Let's call it M complement. You will get a new DFA. Okay, let's call it M complement. Remember, this new DFA will recognize L complement. This new DFA, it will recognize L complement. I told you one very interesting point in our lectures, that is, if this is minimal DFA for language L, if this is minimal DFA and you complement the states, then you will get a new DFA for L complement. And let me tell you, this new DFA will be minimal DFA for L complement. Means if you have minimal DFA for L, then if you complement the states, you will get minimal DFA for L complement. If you start from minimal DFA for L, then you will get minimal DFA for L complement. Okay. Now you might be thinking, sir, is there any way to prove it? So let me tell you the proof I have discussed in this video. I will provide you the link in the description on the YouTube. You can easily see on the YouTube. You can find this. Okay, this GATE CS 2021. You can see this is GATE 2021 question, right? So you can see for this GATE 2021 question, I have already provided with proof the number of states in minimal DFA for L, L complement. Okay, so you can find it. I will provide you the link in the description. So let me tell you the proof. If you want to know the proof, then link you can find in the description or in the pinned comment. Just check the description, or also you check the pinned comment. You will find this video. In this video, I've already proven that number of states in the minimal DFA for L, L complement will be same. Okay, so this is a result. So remember, this is an important result that for any regular language L, okay, for any regular language L, remember, number of states in minimal DFA for L, L complement will be same. Okay, number of states in minimal DFA for L comma L complement is always same. So number of states will always be same. So this is the point that if you have minimal DFA for L, you complement the states in this minimal DFA, you will get minimal DFA for L complement. Okay, so the number of states in minimal DFA for L comma L complement is always same. Okay, so this is the proof I have discussed in this video. You can check it out. Now, let's see the counter example for the remaining options. Okay, let's see what are the counter examples for the remaining options. We already know the answer will be option C. That is fine. Okay, because you can see that for any language, remember, L can be any arbitrary language. L can be any regular language. Okay, if L has K states in the minimal DFA, then L complement, because option C is L complement, right? Option C is L complement. What is L complement? L complement is sigma star minus L. Sigma star minus L. This is L complement. So you can see option C, that is L complement. Okay, and I told you that for any regular language, the number of states in the minimal DFA for L comma L complement is always same. Okay, now let's see the counter example for option A. Can you tell me? Can you give me a regular language L such that the number of states in minimal DFA for L and the number of states in minimal DFA for option A will be different? Can you suggest any language L? So let me tell you counter example for option A. For option A, let me give you the counter example. See, this is very simple. What you can do? Very simple counter example you can take. You can just take this 0 1, that's it. Single string. Yes or no? What you can do? This language you can take. Take this language. Okay. Now, tell me, what is option A? According to option A, what is option A? Let me know. Option A is L minus 0 1. L minus this string 0 1. Yes or no? L minus 0 1. So you can see that, okay, if your language is this single string you have in your language, then what is option A? Then that will be empty. Do you agree? Do you agree? This will become empty. Empty. So tell me, for this option A, the minimal DFA will be how many states? The minimal DFA will have how many states? There will be single state because the language is empty. Okay, and for this language, the minimal DFA will have how many states? Tell me, for this 0 1, the minimal DFA will have how many states? That will be four states. There will be four states. Okay, so you can easily see why four state, because there will be this this state will be there. This dead state will be there, right? Okay, there will be this dead state. So you can see minimal DFA has four states for this language. Okay, but for option A, the minimal DFA has one state. So this is the counter example. Do you agree? Basically, I am saying that if if you take this language, then for this language, minimal DFA has four states. But for L minus this string 0 1, for this language, the minimal DFA has one state. So they are not same. The question is asking must necessarily be same. So this is the counter example for option A. Did you understand? Please tell me. Now let's see the counter example for option B. L union this string 0 1. Can you tell me the counter example for option B? What is option B? See, option B is L union this string 0 1. Okay, so tell me the counter example. Very simple. Again, what you can do? You can take L equal to sigma star minus 0 1. Yes or no? You can take sigma star minus 0 1, or basically you can take empty language. See, you can take empty language. The minimal DFA will have how many states? There will be one state in the minimal DFA. Correct? There will be one state in the minimal DFA. You can easily see. This will be one state in the minimal DFA. Okay. So you can easily see that if you take L equal to 5, then this is a regular language because you have DFA for this language. So minimal DFA has one state. Tell me, for this option B, what will be option B? That will become this. And for this, we have already seen the minimal DFA has how many states? Minimal DFA has 4 states. So are they same? Are they same? No, they are not same. So this is the counterexample for option B. What about option D? L dot L. Can you give me the counterexample for option D? Can you give me counterexample for option D? Tell me. Yes, very easily I can give you counterexample for option D. For example, what you can do? You can take this language. Okay, take this language L. Now tell me what is option D? Option D is L dot L. See, option D is L dot L. Okay, so tell me, if I take this language, then what will be L dot L? That will have single string double A. For this language, minimal DFA has how many states? For this language, tell me, minimal DFA will have 3 states. You can check it out. Okay, there will be 3 states in the minimal DFA. Okay, so basically you can take symbol 0. Symbol 0. So here double 0. Okay, so remember there will be 3 states. Here what will happen? If 0 comes, you accept. If anything else comes, for example, if 1 comes, then you go to this dead state. Okay, and if anything comes, then you go to dead state. So 3 states in the minimal DFA for this language. For option D, in the minimal DFA, how many states? Minimal DFA will have total 4 states. Okay, so again you can notice this is the counterexample for option D, because remember the minimal DFA will be like this, that if 0 comes, you accept. If anything else comes, for example, if 1 comes, then go to the reject this dead state. So this is the idea. I hope this point is clear. So these are the counterexamples for option A, B, D. So the final answer will be option C. Is this point clear? This is a beautiful question in GATE 2021. Basically, in this question, the important result is this, that for any regular language, remember the number of states in minimal DFA for L, L complement is always same. The proof I've discussed in this video, this you can find on the YouTube. You can search this GATE CSE 2021 number of states in minimal DFA for L, L complement. Okay, this video you can watch it, or the link I will provide you in the pinned comment, also in the description, so you can check it out. Let's solve this GATE 2015 question. Let L be language represented by the regular expression sigma star 0011 sigma star, where sigma is 0,1. So the alphabet is binary. What is the minimum number of states in a DFA that recognizes L complement of L? So first of all, the language L is given to you. What is that? That is sigma star, means any string followed by 0011 followed by any string sigma star. So remember, this is like any string sigma star. Okay, any string 0011, then any string. It means containing 0011. Yes or no? This language is basically strings containing 0011. This is the language containing 0011. Now let's create the minimal DFA for this, because the question is asking what are the minimum number of states in the DFA that will recognize L complement. But you already know that the number of states in minimal DFA for L and number of states in minimal DFA for L complement is always same. Yes or no? This point we have already seen that number of states in minimal DFA for L, this will be same. This will always be same. Remember, for any regular language, number of states in minimal DFA for L will always be same as number of states in minimal DFA for L complement. In minimal DFA for L complement. Okay, so they always will be same. So remember what you can do. The question is asking number of states in the minimal DFA for L complement. What you can do, you can find the number of states in the minimal DFA for L. That will be your answer, because for any regular language L, whatever regular language L you take, the number of states in minimal DFA for L, that will always be same as number of states in the minimal DFA for L complement. Okay, L, L complement, they will always have same number of states in the minimal DFA. This we have already seen. Okay, so what you can do, this is the language L that is containing 0011. You can find the minimal DFA and the number of states in this minimal DFA for L, that will be same as number of states in the minimal DFA for L complement. So very easily you can do. Tell me, containing 0011. This is what we want. We want to contain 0011. So I am waiting for 0011. Remember, initially I am waiting for 0011. Okay. So when I will trigger, tell me, when I will trigger, I'm waiting for 0011. So if ones are coming, I will not trigger. If ones are coming, I will ignore. Okay. If zero is coming, then I will trigger. Now I have seen zero. Now I've seen zero. I'm waiting for 011. Okay. Now notice. Now if I see another zero, then I have seen double zero. I'm waiting for 11. If I see one, now I have seen 001. I am waiting for one. If I see another one, now I have seen 0011. Okay, notice one thing. Once I have seen 0011, because I want to contain 0011. Okay, now once I have seen this 0011, now whatever comes, I will accept. So this will become my final state. Now whatever comes, I will accept. Okay, so these are the five states. Now this is not a DFA because see, in this state, for every alphabet symbol, we have created the transition. But in this state, if symbol 1 comes, then what will happen? In this state, remember, in this state, we have seen 0. We are waiting for 011. We want this string 0011. So after 0, if 1 comes, then again I will wait for 0011. Yes or no? In this state, if 1 comes, then whole progress is gone. Then whole progress will be gone. So I will wait for 0011 again. In this state, if 0 comes, then see, in this state, look at this state. In this state, we have already seen 00. We have already seen 00. If another 0 comes, no problem. If another 0 comes, we have no problem because we are waiting for 11. We have already seen 00. If another 0 comes, no problem. Okay. In this state, if 0 comes, then see, look at this state. This state is saying I have seen 001, 001. Okay. See, you have seen 001. You have seen 001 and you are waiting for 1. You are waiting for 1. Okay. I am talking about this state. In this state, I have seen 001 and I am waiting for 1. Now, if 0 comes, remember, I wanted 0011. This is what I wanted. This is what I wanted. Correct? 0011. So tell me, if another 0 comes, then I have to wait for 011. Yes or no? I have to wait for 011. This is what I have to wait for. I have to wait for 011. So remember, in this state, if 0 comes, then I have to wait for 011. Okay. So that's it. This is your DFA. Let me tell you, this is minimal DFA. So this minimal DFA has how many states? There are 5 states. Okay. And let me tell you, the L complement, that will also have minimal DFA with 5 states. How to find L complement? L complement means not containing L complement is not containing 0011. So tell me, for L complement, what you will do? This non-final state, you will make it, this you will make it final, this you will make it final, this you will make it final, and this final state, we will make it non-final. This final state, we will make it non-final. Okay. So you can see for L complement also, the minimal DFA has 5 states. Let me tell you, if this is minimal DFA for L, then this will be minimal DFA for L complement. This is what we have seen. I told you that number of states in minimal DFA for L, that is same as number of states in minimal DFA for L complement. This will happen for every regular language L. Okay. So the answer for this question will be 5. Let's move on now. Let's solve this GATE 1998 question. Let L be set of all binary strings whose last 2 symbols are same. The number of states in the minimal DFA accepting L. See the question. What is the language? The language is, first of all, binary strings means your alphabet alphabet is 0, 1. And what is the language? The language is last 2 symbols are same. Last 2 symbols must be same. Okay, so tell me what are the language? Last two symbols are same. It's simply like this. Anything can come. At the end, either 0 should come, 0 should come, or anything can come at the end, 1 should come. Yes or no? So this type of strings you have in the language L. Okay. Is this point clear? Remember, it is like this. That the language L is like this. That initially anything can come. Sigma star means initially anything can come. At the end, either 0 should come or 1 should come. Okay. At the end, either 0 or 1 should come, because the last two symbols must be same. So this is your language L. Okay. Now let's create the minimal DFA. The question is asking number of states in the minimal DFA. So let me tell you, you can create minimal DFA directly. See, from this language, you can directly create the minimal DFA. You don't have to create NFA, then convert NFA to DFA, then minimize the DFA. You don't have to do that. Okay, we have done a lot of practice that from any regular language directly how to create minimal DFA. For this, we have already done a lot of practice. Okay, so let's use our practice and let's create this. Okay, let's keep track of every state. Okay, I will keep track of the last two symbols. Yes or no? Notice. Initially, what I am doing, focus here. Initially, either I am waiting for 0 or I am waiting for 1 1. Do you agree? Initially, either I am waiting for 0 or I am waiting for 1 1. Okay. If 0 comes, if 0 comes, then okay, if 0 comes, then what I will do? Now I have seen 0. Now I am waiting for 0. Okay, I have already seen 0. Now I am waiting for one more 0. If another 0 comes, now I have ended with 0 0. Okay, what I am thinking? I am thinking that I have ended with 0 0. Yes or no? If 2 0 comes, I am thinking that I have ended with 0 0. Now, if more zeros are coming, no problem. Do you agree with me? I have ended with 0 0. Now, if more zeros are coming, no problem. This is my final state. Okay, because I've already ended with 0 0. So if more zeros are coming, no problem. I'm still ending with 0 0. If more zeros are coming, I'm still ending with I'm still ending with 0 0. Okay. So now you tell me, if the symbol 1 comes, remember, either I'm waiting for 0 0 or I'm waiting for 1 1. So I will trigger because of 0 also, I will trigger because of 1 also. Yes or no? If 1 is coming, then I've seen 1. I have seen 1. I'm waiting for one more 1. Okay. I've seen 1. I'm waiting for one more 1. Because the last two symbols must be same. Means either the last two symbols can be 0 0 or the last two symbols can be 1 1. So in this state, if 1 comes, then I'm waiting for one more 1. Okay. Now, if 1 comes, then what I will do? Now I'm thinking that I've ended with 1 1. In this state, I have ended with 1 1. In this state, I have ended with 0 0. Okay. Now, I am thinking that I have ended with 1 1. So if any number of ones are coming, I will ignore. Yes or no? Because I've already ended with 1 1. So if more ones are coming, I'm still ended with 1 1. If more ones are coming, then I've still ended with 1 1. So there will be self loop here. Very simple. So far, everything is clear. Now tell me, this state is done because in this state, for every input alphabet, I've created the transition. You tell me, in this state, if 1 comes, then what I will do? Where should I go? In this state, if 1 comes, remember, in this state, I am waiting for 0. I've already seen 0, but tell me, after 0, if 1 comes, then no problem. I will wait for 1 1. Do you agree? See, either I am waiting for 0 0. Notice, either I want this or I want this. Do you agree? Either I want this or I want this. Either I want 0 0 or I want 1 1. So now you tell me, after zeros, if 1 is coming, just tell me this point. See, I am saying either I want this or I want this, means either I want 0 0 or I want 1 1. So tell me, after 0, if 1 comes, no problem, no problem. I will wait for 1 1. Are you getting my point? See, after 0, if 1 comes, then no problem. I will wait for this. Do you agree? So this is what I'm saying, that in this state, if 1 comes, then I will wait for 1. This state, if 1 comes, I will wait for 1. Correct? Similarly, you tell me, in this state, if 0 comes, then what I will do? See, in this state, means you have already seen 1. After 1, after this one, if 0 comes, after this one, if 0 comes, no problem. I will wait for, I will go for this. Remember, either I have to go for this or I have to go for this. Either I will go for double, go for double one. Now, if after one, after this one, if 0 comes, then I will go for double zero. Okay, correct. Then I will go for double zero. So very simple that in this state, if 0 comes, I will go for double zero. Okay. In this state, I've ended with 1 1. If 0 comes, where I will go? In this state, I've already ended with 0. I've already ended with 1 1. Means I am thinking that I've ended with 1 1. I am thinking I've ended with 1 1. Now tell me, if 0 comes, then no problem. I will go for 0 0. Yes or no? So basically, in this state, if 0 comes, no problem. I will go for double zero. Similarly, in this state, if 1 comes, I will go for double one. Okay. So tell me, is this point clear? So in this state, if 1 comes, then I will go here. Okay. So that's it. That's it. This also will be your final state because either you want to end with 0 0 or you want to end with 1 1. So these will be your final state. Now tell me, is this minimal DFA? On your screen, is this minimal DFA? Is this a minimal DFA? We got the DFA. You understood the DFA, right? Yes or no? How to create the DFA? Did you understand? Remember, either I want double zero or I want double one. This is the only point. Either I want double zero or I want double one. That's it. I want to end with double zero or I want to end with double one. So this is the DFA I can create. Now tell me, after creating this DFA, let's verify, is this minimal? Is this minimal? So tell me which states you will check. Which states are you going to check? You will check the final states. Also, you will check the non-final states. These final states, are they equivalent? They are distinguishable by whom? Look at these states. Let's call it Q, let's call it P, P comma Q. They are distinguishable by 0. Yes or no? You can notice this state P on 0 going to non-final, this state Q on 0 going to final. So these are definitely distinguishable. You cannot merge these two states. What about this state and this state? Are they distinguishable? These two states, are they distinguishable? Yes, they are distinguishable by 0. You can notice this on 0 going to final, this on 0 going to non-final. What about these two? Are they distinguishable? Yes, they are distinguishable by 1. This on 1 going to final, this on 1 going to non-final. Are these two distinguishable? What about these two? Yes, they are also distinguishable by 0. This on 0 going to final, this on 0 going to non-final. So can I say that this is a minimal DFA? Yes. Yes, this is a minimal DFA because they are not equivalent. They are not equivalent. All the states are distinguishable from each other. So this is a minimal DFA. So minimal DFA has 5 states. So the answer for this question will be 5. Is this point clear? Please tell me. So this is a nice question. GATE 1998 question. From the language, you can directly create the DFA. First, you directly create the DFA. Then you verify is it minimal or not. After creating the DFA, you minimize this, or I can say you verify is it minimal. Okay, so when you verify, you will find that yes, this is minimal. So the answer will be 5. Okay. Let's solve this GATE 2007 question. Consider the following DFA in which S0 is the start state. This S0, this is the start state. S1, S3 are the final state. These two are the final state. What language does this DFA recognize? So let me tell you, this question you can solve by many different methods. But the best method, whenever the question is asking which language is recognized, 4 languages are given to you. This DFA will recognize which language. Then the best method, let me tell you, that is option elimination. You can simply eliminate the options. Okay, so let's eliminate the options. Tell me. Let's see option A. Can you give me the counterexample for option A? Option A is saying what this DFA recognize. Option A is saying every string of x comma y. Option A is saying every string is recognized. Is this true? Is this true? Every string is. No, you can easily see that which are the rejected strings. Tell me which are the rejected strings by this DFA. This DFA is rejecting empty string. This is also rejecting what? This is rejecting XY. XY string is rejected. You can easily see that YY is rejected. So the option A is gone. Option A is saying that all strings are recognized, but this is false. So option A is gone. Okay, so you can see for option A, the counter example is these strings, for example, XY. Okay, these are the counter example like XY, YY. These are the counter examples because these strings are not accepted by this given DFA. Tell me, what about the next? See, option B. Option B is saying all strings of XY which either have even number of X and even number of Y or odd number of X and odd number of Y. So tell me, is it correct? See, you just look at the DFA and tell me some accepted strings and some rejected strings. When you look at this DFA, you tell me some accepted strings and some rejected strings. You tell me. Anyone? Give me some accepted strings and give me some rejected strings. Then we will check the options. So give me. What are some accepted strings? Like for example, X is accepted string. Correct? For example, triple X, this is accepted string. Okay. Double X is rejected string. Empty string is a rejected string. Double Y is rejected string. You can easily see Y is accepted string. You can see that XXY is accepted. XXY that is accepted. You can see YYX is accepted. Okay. And you can see that XY is rejected. You can see YX is rejected. So like this. Okay. I hope this point is clear. So you can easily see that option A is gone, that you already know. Tell me, what about option B? Option B is saying that every string of XY which has even X, even Y or odd X, odd Y. Tell me, this option is gone because of what? See, this option is gone because of this YX. Because this is rejected, YX is rejected. See, this has even X, even, odd X, odd Y. Look at this string. This has odd X, odd Y. But this is not accepted. Okay, so the counter example, what is that? Counter example is this string XY. Do you double X, double Y? This is rejected. So you can consider this also as a counter example. Because double X, double Y, that is rejected. So this is also counter example. What about option C? Tell me, what about option C? All strings of XY with equal number of XY. This is also gone, right? Why this is gone? Because what is the counter example? That is double X, double Y or XY. Okay, the counter example is XY, double X, double Y. So these are the counter examples. Correct? What about option D? So automatically option D will be correct. And you can easily see option D is actually correct because this is saying either even X, odd Y or odd X, even Y. You can easily see here odd X, even Y, here odd X, even Y, here even X, odd Y, here even X, odd Y, here even Y, odd X. Okay. So you can easily see option D is correct. For option C, a student is asking for option C, what is the counter example? Option C is saying that every string which has even X, even Y, every string which has equal X, equal Y is accepted. But this string is rejected. Equal X, equal Y. This string is rejected. Do you agree? See, option C is saying that equal X, equal Y are accepted. Option C, that is saying all strings of XY which have equal X, equal Y, they are accepted. But this is rejecting XXYY. This is rejected. You can simply see that, for example, here equal X, equal Y, but this is also rejected. So these are the counter examples for option C. Is this point clear? So option C counter example we got. So the answer will be automatically option D. Is this point clear? Let me know. So for this question, answer is option D. And actually, this is very analytical. If you want to solve this question by analysis, then also you can easily solve. Notice one thing, there are many methods to solve this question. A student is asking, is it possible to create a DFA for option C? The answer is no. Okay, the answer is no, because C option C is saying all strings of X and Y which have equal number of X and Y. Let me tell you that this is actually not regular. For this, you can never create a DFA. Let me tell you, forget about this DFA. You can never create a DFA. Actually, for this, no DFA exists. Okay, but don't worry, this is not the answer. Option C, that is not the answer. Actually, for option C, you can never create a DFA. The option C is actually not regular, means no DFA exists for option C. Okay, but let's focus on option D now. Actually, if you do the analysis of this, then you will find that option D is correct. Why option D is correct? See, what is S0? Focus on S0 and tell me what S0 tells you. How many X, how many Y? Remember, your alphabet is X, Y. Our alphabet is X, Y. Now you tell me about S0. What S0 is telling you? See, in S0, can you notice you have even X, even Y? In S0, you have even X, even Y. Can I say? In S0, you have even X, even Y. You can notice in S0, you have even X, XX, Y. You will always have even X, even Y. Okay, what about S1? Focus on S1. Tell me, in S1, can you notice that you have odd X, even Y? Very easily, you can focus that you have odd X and you have even Y, because you can see odd X, but you can see Y. So that is even Y. You can easily see odd X, even Y. What about S2? What about this S2? S2 has odd X, odd Y, odd X, odd Y. And what is S3? Look at S3. That is even X, odd Y. That is even X, odd Y. Okay. This is S3. So what are the final states from here? The final states are S1 or S3. These are the final states. So tell me, because these are final. Final states are S1 or S3. So tell me what your answer will be. That will be odd X, even Y. So the language will be like this. The language will be odd X, even Y, or or even X, odd Y, or even X, odd Y, or even X, odd Y. Okay. So the final answer will be option D. Is this clear? You can see even X, odd Y, or odd X, even Y. Okay. So that is correct answer. Is this point clear? But let me tell you one thing, that for this language, is this the minimal DFA? What do you think? See, you know, this is your language. You found the language. The language is like this. The alphabet is X, Y, and the language is either you have odd X, even Y, or or even X, odd Y. I'm asking this, that in one word, what can I say for this type of strings? For this type of strings where either you have this or this, in one word, can I say something? For this type of languages, for this type of strings, can I say something? We have odd X, even Y, or even X, odd Y. In simple words, can I say that we have odd length strings? Can I say? Can I say we have odd length strings? Please tell me. Can I say this is your language? Your language is odd length strings. Do you agree with me? You will have odd length strings. Please tell me. So very easy. You can see this is your language. Your language is odd length string. That's it. So tell me what will be minimal DFA for this? So your language is odd length strings. So minimal DFA will have how many states? Okay, so the minimal DFA, let me create. that will have two states. Okay, very simple. There will be two states, even, odd. Okay, we want odd, so that will be like this. X comma y, you go here, and like this. So this will be your answer. Actually, minimal DFA will have two states. Okay, for this question, the minimal DFA will have two states. So that's it. This is very simple question. I hope you understood. The answer will be option D. Now let's move on. Let's solve this GATE 2012 question. See, the question is saying consider the set of strings on 0, 1 in which every substring of three symbols has at most two zeros. For example, these strings are in the language, but this string is not in the language because every substring of three symbols must have at most two zeros. But here you can notice that here this is a substring of three symbol and it has three zeros. So you can easily see that this string does not belong to the language. Now the question is saying that a partially complete DFA is given to you. A partial DFA is given to you. Okay, and the missing transitions we have to find out. Okay, see, very simple point. This partial DFA is given to you, but we have to find the missing transitions. Is there any missing transition here? Do you see any missing transition in this? Yes. In this state, what will happen if 0, 1 comes? In this state, if 0 comes, what will happen? In this state, if 0 comes, what will happen? In this state, if 1 comes, what will happen? So there are missing transitions. Do you agree? We have missing transitions. Now the question is asking, what are the missing transitions? Options are given to you. 4 options are given to you. Okay, let's solve this question. This is a very simple question, let me tell you. First, you understand the language. The language is saying that strings of 0, 1 where, read this line. Tell me in simple words what this line is telling you. Every substring of three symbols has at most two zeros. Tell me what this line is telling you. Every substring of three symbols has at most two zeros. Can anyone tell me what this line tells you? Every substring of three symbols. See, if you take any three symbols, okay, any substring of three symbols you take, then they will have at most two zeros. Means you can 0, 0, 0. Do you the given language is not containing triple zero? Not containing triple zero. See, this line is given to you in the question that you have a language on the alphabet 0, 1, basically set of binary strings in which every substring of three symbols has at most two zeros. Actually, what this line means, let me tell you. This line simply means that, okay, we are not containing triple zero substring. This is what this line means. Okay, nothing else. This fancy line, this simply means that not containing triple zero substring. That's it. We are not containing triple zero. Okay, this is the point, because remember the question is saying that if you take any three symbols, okay, like this is your string, and if you take any three consecutive symbols, any 3-bit substring if you take, okay, any three symbol substring you take, then remember we should have at most two zeros. At most two zeros. What it means? It means this is not allowed. Triple zero is not allowed. Okay, is this point clear? So the same thing I am telling you, that this is not allowed means this fancy line in the question, this simply means that not containing triple zero substring. Okay. So let me tell you one more thing, beautiful thing. For this language, actually the minimal DFA will have how many states? Can anyone tell me? For this language, your language is not containing triple zero substring. This is your language. For this language, tell me the minimal DFA will have how many states? If you notice the minimal DFA actually, the minimal DFA for this language, the minimal DFA for this language actually has how many states? There will be total 4 states. Okay, so remember this given DFA is not a minimal DFA. Is this point clear? This simple observation you can make that this is not a minimal DFA. Let me tell you. Okay, so this is just a DFA, but this is not a minimal DFA. Is this clear? This DFA that is given to you, this is not a minimal DFA. This is what I'm saying. Is this point clear? Let me know. Okay, so remember the question is saying that a DFA is given to you. The question is not saying that it is minimal DFA. It is not a minimal DFA because for this language, every substring of three symbols has at most two zeros. This simply means not containing triple zero substring. For this language, if you create the minimal DFA, the minimal DFA will have, there will be four states in the minimal DFA. So this DFA that is given to you, this is just a DFA, but this is not a minimal DFA. Now we have to find what are the missing transitions. Now this question has become very simple. So your language, we already know that this. Okay, so this line, what this line means? This line simply means not containing triple zero. Not containing substring triple zero. Okay, so now we can easily create the missing transitions. Let's see what are the missing transitions. Tell me. For example, see, look at this state. See, this state is already over. Do you agree with me? In the initial state, already on every input symbol, we have created the transition. Do you agree? So, which states are already complete? Can anyone tell me which states are already completed? Which states are already completed? Means which state have no missing transitions? Which are the completed state? You can see the initial state is completed state. This initial state. Okay, you can see this state is completed because in this state, look at this state. In this state, for every input symbol, we have created the transition. So this is completed state. This is also completed state because in this state, for every alphabet symbol, we have created the transition. Okay, so this is also completed state. Next, is there any other completed state? Yes, state Q is completed. State Q is completed because in the state Q, on every input symbol, we have created the transition. So this state Q is also completed. Now, which states are not completed? You can see these four states are not completed. Yes or no? Is this clear? Okay, so let's see one by one. In this state, double zero. This state is telling you that you have seen double zero. If zero comes, then what should happen? See, this is your dead state because this is non-final state. See, this is your non-final state with self self loop. So this is your dead state, right? You can easily see this is your dead state because this is a non-final state with every symbol is self loop. Okay, so this is your dead state. So you can see, remember, I don't want triple zero. Please notice. Okay, not containing triple zero. Okay, I don't want triple zero. So after 00, if another zero comes, where should I go? Tell me. After double zero, if another zero comes, then I should go to dead state because now there is no chance of acceptance because I don't want triple zero. I do not want triple zero. Now, if triple zero comes, then there is no chance of acceptance. So I should go to dead state. So this is what I'm saying that in this state, if in this double zero, if symbol zero comes, then I should go to dead state. Very simple. Yes or no? So this is what I'm saying that in this state double zero, in this state, if symbol zero comes, then I should go to state Q. Yes or no? Here, remember, these are the states. Here also I am writing the states. And here also I am writing the states. Okay, so you can easily see in this state, if this symbol comes, this is the symbol. Okay, so I can say that in this state, if symbol zero comes, then I will go to state Q. Okay, is this point clear? Let me know. So very simple point. So which options are gone? See, four options are given to you. Which option is gone? You can notice this option A is gone. Why this option A is gone? Because you already know that in this state 00, please focus. In this state 00, if symbol zero should come, then I should go to state Q. Yes or no? This should happen. If zero symbol comes, then I should go to state Q. This is also gone. Yes or no? Because of this. So these options are gone. Now these options are remaining. These two options are remaining. So now let's see the next. Now you tell me, in this state double one, if symbol zero comes, where should I go? You tell me. In this state double one, I'm asking, in this state double one, if symbol 0 comes, where should I go? I should go to 1 0. Very simple. This is very simple because see, all the states are already numbered, or I can say all the states are already labeled. Every state is labeled, you can easily see. Notice what this state is telling you. This state is telling you so far we have ended with 1 1. So far we have ended with 1 1. Yes or no? So far we have ended with 1 1. This state is telling you so far we have ended with 0 0. So far we have ended with 0 0. Okay, so these states are telling you something. Every state is labeled if you notice. If you notice, every state is labeled. Okay, so you can just solve this question very easily that in this state double one, in this double one state, if symbol 0 comes, then where I will go? Then I will go to state 1 0, right? Okay, so this is what I'm saying that in this state, if symbol 0 comes, I will go to 1 0. Okay, so this is what I can say that in this state double one, I will go to state 1 0 on symbol 0. Okay, so like this. Now, what about the next? So let's see which option is gone. Okay, from this state on symbol 0, I will go to 1 0. So tell me which option is gone. Tell me. Here you can notice. So far, yes, this option C is also gone. Do you agree? Because from this state on symbol 0, I should go to 1 0. So option C is also gone. So finally, your answer will be option D because all other options are eliminated. So the answer will be option D. But let me check the remaining transitions. Okay, now you tell me in this state. Okay, if 0 comes, I will go here. That you already know. Now in this state, if 1 comes, where I will go? Tell me. In this state double 0, if symbol 1 comes, where I will go? I will go to 0 1. Yes or no? Very simple. So this is what I am saying that in this state, if symbol 1 comes, I will go to 0 1. Okay. What about the next? What else is remaining? You can see this is remaining. In this state 0 1, if 1 comes, where I will go? In this state. In this state 0 1, if 1 comes, then where I will go? I will go to double 1. Okay. So this is what I am saying that in this state, if 1 comes, I will go to double 1. Okay. Next, tell me the next. For example, in this state 1 0, in this state 1 0, if 0 comes, where I will go? If 0 comes, where I will go to double 0. Yes or no? So in this state 1 0, if 0 comes, I will go to double 0. Okay, that's it. This is your answer. So finally, you can easily see your answer will be option D. Let's check option D quickly. Option D, you can notice in this state double 0, if symbol 0 comes, you will go to dead state. Okay, that is correct, right? Yes or no? In this state double 0, if symbol 0 comes, I will go to dead state. Q is the dead state. So that is correct. Next, you can see in this state 0 1, if symbol 1 comes, where I will go? I will go to double 1. Okay, if symbol 1 comes, I will go to state double 1. That is also correct. Next, in this state 1 0, if symbol 0 comes, I should go to double 0. Yes, that is also correct. Next, you can see in this state double 1, if symbol 0 comes, I should go to 1 0. I should go to 1 0. That is also correct. So the answer will be option D. This is a very simple and beautiful question, let me tell you. Okay, this is extremely simple question if you think about it. Let's move on now. Let's solve this gate 2000 question. Construct as minimal finite state machine that accepts the language over 0, 1 of all strings that contain neither substring 00 nor substring 11. Let me tell you, this is also another beautiful question, but think about what strings will be there in the language. See, just think about it. The question is saying that you have alphabet 0, 1, your binary alphabet, and the language is given to you. The language is like this: neither containing double 0 nor containing double 1. Neither containing double 0 nor containing 1. Can you tell me which type of strings will be there in the language? Anyone want to suggest? Anyone want to suggest? If you have, this is the language neither containing double zero nor containing double one. Because see, all strings, read this, all strings that contain neither double zero nor double one. I don't want double zero, I don't want double one. So which type of strings will be there in the language? Very good. A student is saying alternative 0, comma 1. That's very good. Excellent. Because remember, the question is saying neither containing double zero nor containing double one. So let's create the string. If I start from 0, can the next symbol be 0? Can the next symbol be 0? No, no, no. The next symbol will be 1. Okay. If this symbol is 1, can the next symbol be 1? No, the next symbol cannot be 1. The next symbol will be 0. Now, can the next symbol be 0? No, the next symbol cannot be 0. The next symbol will be 1. So, can you notice in this language, I have alternative 0, comma 1s. I have alternative 0, comma 1s. It will be like this. In this language, I have this type of strings. Okay, I have empty string because yes, empty string doesn't have 0, 0. Empty string doesn't have 1, 1. So, there will be empty string. I will have 0, I will have 1. But remember, I will have 0, 1, I will have 1, 0. I will have this type of string like 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, like this. Alternative zeros, ones. Okay, is this point clear? Please tell me, did you understand the language? So remember, in this language L, I will have alternative 0, comma 1s. Okay, is this clear? So your language actually has alternative 0, comma 1s. It's like this. There will be empty string, there will be 0, comma 1 because they don't contain 0, 0, they don't contain 1, 1. But after that, it will be like 0, 1, 1, 0. Okay, how many three length strings can be possible? These are the three length strings possible. How many four length strings possible? These are the four length strings possible. How many five length strings possible? These are the five length strings possible. Okay, I hope you are getting. So if I ask you, how many 10 length strings are possible? Tell me in this language L, how many 10 length strings are there? How many 10 length strings are there? Only two strings. Yes or no? How many 10 length strings? Only two strings are there. Okay. Anyway, now the question is asking for this language, we have to create a minimal DFA. Okay. Remember, I told you that minimal FA simply means minimal DFA. Yes or no? Okay. Whenever the question is asking minimal FA, then the question is simply asking minimal DFA. Okay. So now let's see what will be the answer here. So let's create the minimal DFA for this language. You already understood what is the language. So your language is alternative 0, comma 1s. Alternative zeros, comma 1s. Okay. And remember, there will be empty string also. There will be empty string. There will be 0, comma 1 and like this. This type of strings you have. Okay. So let's create the DFA now directly. So what we will do, notice the DFA is actually very simple. Okay. The initial state will be final, no problem. Yes or no? Because I want to accept empty string. And you already know that in the DFA, empty string is accepted if and only if initial state is final. So I want to accept empty string because remember, empty string does not contain 0, 0. Empty string does not contain 1, 1. So this should be accepted because the language is saying that we don't have 0, 0, we don't have 1, 1. So this string doesn't have 0, 0. This string doesn't have 1, 1. So this string should be accepted. Okay, now notice if 0 comes, please now focus here. See, if 0 comes, now so far what are the last symbol? Tell me, I will only take care of the last symbol. Can you notice? If I want to create DFA for this language, what is the idea? Let's see the DFA idea, or I can say minimal DFA. I will directly create the minimal DFA. So tell me what the idea? The idea is very simple. Can you notice? I will only take care of the last symbol. Can you notice? I will only take care of last symbol. Means I will only keep track of last symbol. I can say I will only keep track of last symbol. Keep track of means I will remember what was the last symbol. Do you agree with me? Keep track of only Last symbol that I have seen. What is the reason? Can anyone tell me? What is the reason? Because remember, okay, only the last symbol I will see. For example, if the last symbol was 1, then what should be the next symbol? If the last symbol was 1, what should be the next symbol? The next symbol should be 0. If the last symbol is 0, what should be the next symbol? The next symbol should be 1. If the last symbol is 1, what should be the next symbol? The next symbol should be 0. If the last symbol is 0, then the next symbol should be 1. So do you agree with me that I will only keep track of, I will only remember what is the last symbol we have seen so far? Do you agree with me? We will only remember what is the last symbol we have seen so far. Yes or no? Just remember what are the last symbols you have. For example, if this is your last symbol seen so far, then the next symbol should be 0. Okay, that's it. So this is the simple idea that in the initial state, if 0 comes, then I will say that the last symbol was 0. Yes or no? Can I say the last symbol was 0? I can say the last was 0. Last symbol 0. Last symbol was 0. Okay, now you tell me, if symbol 1 comes in the initial state, if symbol 1 comes, where I will go? Remember, this also will be final state because I want to accept string 0. I want to accept string 0, so this will be final state. Now remember, if the in the initial state, if symbol 1 comes, then I am thinking that last symbol I have seen is 1. Yes or no? Here I will remember the last symbol was 1. This is what I will remember. That last symbol was 1. Yes or no? Now this is very simple. In this state, if 0 comes, where should I go? After 0, if another 0 comes, where should I go? I should go to dead state because now there is no chance of acceptance. Okay, if you have double 0, notice after 0, if another 0 comes, now there is no chance of acceptance. I will go to dead state. Similarly, in this state, remember this will be final state because I want to accept 1. This string 1 I want to accept, so this will be final state. Now remember, in this state, if another 1 comes, after 1, if another 1 comes, I will go to dead state because there is no chance of acceptance. Now something interesting. In this state, the last symbol was 0. If 1 comes, where should I go? After 0, if 1 comes, where should I go? Remember, this state is saying, what this state is saying? This state is saying that last symbol was 0. If 1 comes, then the last symbol is 1. If 1 comes, then the last symbol is 1. And if in this state, if 0 comes, this state is saying the last symbol was 1. Okay, if 0 comes, then the last symbol will be 0. Okay, that's it. This is your minimal DFA. Let me tell you, this is minimal DFA. This has 4 states. Okay, can you notice this is minimal? Can anyone tell me why this is minimal? Because you can easily see that, see, these are final states, this is non-final state, so we have to check these are distinguishable or not. Are they distinguishable? These two, are they distinguishable? Tell me. Look at these two states. Are they distinguishable? These two. These are final states. Are they distinguishable? Yes. They are distinguishable by 0. Because this state on 0 going to non-final, this state on 0 going to final. What about these two states? Are they distinguishable? Yes. They are distinguishable by 1. This state on 1 going to non-final, this state on 1 going to final. What about these two states? Are they distinguishable? Yes. This on 0 going to non-final, this on 0 going to final. So all the states are distinguishable. So finally, this is a minimal DFA. This has 4 states. Okay. The answer will be minimal DFA has 4 states. So this is a beautiful question. And for this question, the answer will be number of states 4. Okay. Is this point clear? Please tell me. So, so I hope you understood how to create the minimal DFA directly. If a language is given to you, you just think about the idea. You first understand the language, which strings belong to the language, which strings do not belong to the language. So when you understand the language, then you can easily create the minimal DFA directly from the regular language. You don't have to create, first you create NFA, then you convert to DFA, then you minimize the DFA. You don't have to do that. Okay. From the regular language, you can directly create the minimal DFA. We have done a lot of practice and I hope you understood this also. Please tell me, did you understand from this language how to create minimal DFA directly? Did you understand? We only have to keep track of last symbol, because remember, if you know that last symbol is 1, then next symbol should be 0. If the last symbol is 0, next symbol should be 1. If the last symbol is 1, next symbol should be 0. So you only have to keep track of last symbol. You only have to remember the last symbol. So the last symbol either can be 0 or the last symbol can be 1. So like this, easily you can create the minimal DFA directly. Okay, let's move on now. Let's solve this GATE 2008 question. Consider below two finite automata. Two DFA are given to you. DFA Y, DFA Z. Two DFA are actually given to you. The alphabet is AB. You can easily see. In this DFA, we have two states. State 1 is initial state. State 2 is final state. In this DFA also, you can see we have two state. State 1 is initial state. State 2 is final state. 2F means 2 is the final state. 2F means this is the final state. And this means this is the initial state. So there are two DFA. Okay, remember F indicates final state and this arrow indicates start state. So we have two DFA. Now the question is asking which of the following represents the product automata Z cross Y. Okay, we have to find which of them is product automata Z cross Y. Okay, now I want to ask you one question. The question is asking that product automata Z cross Y, but we know that the product automata we can create for union, intersection, set difference, symmetric difference, yes or no? We can create product automata for many operations, union, intersection, set difference, symmetric difference. Then tell me, for which operation they are asking? Can anyone tell me? In this question, did they mention, are we creating product automata for union or are we creating product automata for union intersection? For which operation are we creating product automata? Is that given in the question? Did you understand what I'm asking? I'm asking that, see, product automata you can create for union, intersection, set difference, symmetric difference. For different operations, you can create the product automata that we already know. Now, in this question, is it given that we are creating the product automata for which operation? Is this given? This is not given. Let me tell you why this is not given. When it is not given that for which operation you are creating the product automata, then by default we are creating product automata for intersection. Okay, so remember, by default we are creating the product automata for intersection operation. Okay, this is basically by default assumption. If the operation is not given, that for which operation we are creating the product automata, then the by default operation is intersection. The by default operation is not union, not set difference, not symmetric difference. If you are creating product automata and the operation is not given to you, for which operation are you creating the product automata, then by default the operation is intersection. Okay, is this point clear? Now let's solve this question very easily. You can solve it. So two DFA are already given to you. We have to create a product automata Z cross Y. First of all, let me tell you that Z cross Y, Y cross Z, both are same. Okay, let me tell you all the doubts that you might be having. See, some students might be having these doubts, sir, Z cross Y, is it same as Y cross Z? Yes, in the product automata, they are same. Okay, in the product automata, they are same in the product automata. They are same in the product automata. In the product automata, basically, this does not matter. Are you calling it Z cross Y or are you calling it Y cross Z? This does not matter. Okay, this is the first thing. The second thing, remember, when operation is not given, when operation is not given, when operation is not given, then remember, then by default, product automata is created for intersection operation. By default, remember, if operation is not given, then by default, this product construction we do for this product automata, this product construction is done for intersection operation. Okay, so these are the two doubts that many students might be having. Sir, what is the operation for product automata? Because we can create product automata for union, intersection, set difference, for many operations we can create. So what is the operation here? So let me tell you, the by default operation is intersection operation. Okay, and Z cross Y is same as Y cross Z. Now let's solve this question very easily. You can try this question, you can easily solve. Okay, remember the DFA are given to you, two DFAs are given to you. The first DFA is y. Okay, in the DFA y, what they have given in the DFA y, let me write it. DFA y is like this. There are two states, 1 comma 2. Okay, there are two states, 1 comma 2. One is the initial state, two is the final state. On symbol AB, where are we going? So you can see we are going to 1 to 2 1. Okay, we are going to 1 to 2 1. So this is the DFA that is given to you. This is DFA y. And what are the DFA z? In the DFA z also you have two states. Okay, state 1, state 2. State 2 is the final state. On AB, where are we going? We are going to 2 to 1 1. 2 to 1 1. Okay. Now the question is asking what is the product automata? So very easily you can do. Tell me in the product automata, what are the states? Do you know what are the states in the product automata? Tell me. If you have two DFA, if you have DFA, for example, M1, M2, okay, if you have two DFA, then what you can do, you can create a product automata. You can create a product DFA. What you can do, you can create a product DFA. So this M1 cross M2, this product DFA you can create. This we already know. We create this for different operations. Either you can create it for intersection or for union or for set difference or for symmetric difference. Okay. And here I told you that this is default. If nothing is given, this is default. If no information is given, this is default. Okay. And in this product automata, what are the states? Tell me what are the states in this? The states will be ordered pairs of states of M1, M2. Yes or no? The states will be like this. The states will be like this, P, Q, where P is the state of M1. This is the state of M1, where Q is the state of M2. Yes or no? These will be the state. Do you agree with me? Okay, so very simple. These are the states in the M1 cross M2. In this M1 cross M2, the states are ordered pairs of states of M1, M2. So this type of states will be there. Okay, now let's see here. So the product automata will have total 4 states. Do you agree? Okay, now we are creating Z cross Y. Okay, so let's create the Z cross Y. There will be total 4 states. What will be the initial state? Tell me. What will be the initial state? Let me know. So remember, there will be total 4 states. The states will be like this. The states are ordered pairs of states of Z comma Y. Okay, so it will be like this. This will be the state Z1. Okay, comma Y1. This will be the initial state. Do you agree with me? This will be the initial state. Okay, the initial state will be basically both the automata will be in the initial state. If you remember, I told you the idea of product automata. If you remember in the lectures, we have seen what is the idea of product automata. Tell me what is that? See the idea of M1 cross M2, where M1, M2 are DFA. Remember here M1 is a DFA and M2 is a DFA. Okay, and if you remember in the lectures, we have already seen the idea of product automata, that is running simultaneously, running in parallel. Yes or no? Running in parallel. This is the idea of product automata, that both the DFA will run in parallel. Remember, both the DFA. Okay, both the DFA will do like this. Like for example, if this is your string W, then remember both the DFA, this DFA M1, also this DFA M2, both the DFA will run in parallel. Okay, so this DFA M1 will also run and this DFA M2 will also run. They will run in parallel. And remember, where they will start, it's like a race. It's like a race. Let me tell you, it's like a race. They are running in parallel. And where they will start, tell me, they will start in their initial state. Like this will start in its initial state and this will start in its initial state. Okay, both the DFA will start in their own initial state and they will run parallel. Like after this symbol, what will happen? For example, let's assume this symbol is A, then this will make its transition and this will make its transition. So they will go to a new state. Like for example, this can go to state Q1, this can go to state P1. So like this. So this is the idea. Basically, this product automata, this M1 cross M2, this will start in this state. The starting state will be this. Both the DFA will start in their own initial state. Then they will make transitions. They are running parallel, basically. This is the idea, running in parallel. Okay. Now you tell me, for intersection, when this W will be accepted, tell me when W will be accepted for intersection. I'm asking for intersection operation. For intersection, tell me when W should be accepted. Let me know. W is accepted. When W is accepted? Very simple. W is accepted if both of them should go to final state. Yes or no? Very simple. Remember, W should be accepted for intersection. Intersection means common string. Means this DFA M1 should also go to final state and this DFA should also go to final state, right? They should end in the final state. Means this also should end in final state. This also should end in final state. So remember, W will be accepted if and only if both M1 comma M2 end in final state. Okay, so this is the idea. Okay, now if you understood the idea, you can easily see that in this Z cross Y, the initial state will be, both the DFA will be in their own initial state. Means Z will be in its initial state and Y will be in its initial state. So I can call it like Z1 Y1. Okay, if there is no confusion, so that there is no confusion, I am calling it Z1 Y1. That this DFA Z is in its initial state and DFA Y is in its initial state. Okay. Now you tell me, the another state will be like this. The another state will be Z1 Y2. The another state will be Z2 Y1, and the another state will be Z2 Y2. Yes or no? These will be the four states in this cross product. In this product automata, there will be four states. These are the ordered pairs of states of Z comma Y. Okay, now you tell me, this state, initial state on symbol A, where it will go? This initial state on symbol A, where it will go? Please tell me. So you can see where Z will go on A, where this DFA, this on A, from state 1 on A, we are going to state 2. Yes or no? So we will go to Z2. We will go to Z2, and where this will go on A, so this will go to Y1. So Z2 Y1. So I can say on symbol A, you will go here. Z2 Y1. Very simple. Okay, on symbol B, where we will go? So you can see this Z. Okay, from here on B, we are going to 2. So Z2. Okay, Z2, and here also Y2. Yes or no? Z2 Y2. So remember, on symbol B, where are we going? On symbol B, we are going to Z2 Y2. Is this point clear? Okay, now tell me, what about this state? Where are we going on symbol A? On symbol A, we are going to Z2. Okay, remember, from Z1. From Z1, I am asking from Z1 on symbol A, we will go to Z2, and from Y2, on A, we will go to Y2. So Z2 Y2. So okay, on symbol A, we will go to Z2 Y2. From this state on B, where we will go? From Z1 on symbol B, we will go to Z2. Okay, Z2, we will go to Z2, remember. And what about Y? Y2 on B, we will go to Y1. So Y1 Z2. Okay, Y1 Z2. So it will be happening like this, that okay, we will go to this state, Y1 Z2 on B. Okay, now you tell me, what next? See, just to save this, what I can do, let me make it Z2 Y2, so that these I don't have to do. Okay, so for a moment, so let me call it Z2 Y2, and let me call it Z2 Y1. Okay, now you can see that it will happen like this, that this will go, okay, AB. Sorry. Yeah, it was correct. No problem. Okay. Anyway, so because if I make it B, then this A will come. Okay, this like this. Okay, no problem. So this is correct. Okay, now you tell me. In this state, Z2 Y1 on symbol A, where we will go? Z2 Y1. See, Z2 on symbol A. On symbol A, we are going to Z1, right? We are going to Z1. So Z1 is fixed. Now, Y1 on A, it is going to Y1. So Z1 Y1. Yes or no? On symbol A, we will go to Z1 Y1. On symbol B, where we will go? This Z2 on symbol B, it will go to Z1. Okay, so in Z1 we will go, and Y1 on symbol B, it will go to Y2. So Z1 Y2. Okay, so remember, on symbol B, we will go here. On symbol B, we will go here. Okay, what about this state? Z2, Y2. On symbol A, where we will go? This Z2 on symbol A, it will go to Z1, and Y2 on symbol A, it will go to Y2. So Z1, Y2. Yes, correct. Z1, Y2. So on symbol A, we will go to this state. And on symbol B, where we will go? We will go to Z1, Y1. Okay, Z1, Y1. On symbol B, we will go to Z1, Y1. Okay, that's it. Now, can you create? See, the question is asking which of them is the product automata. So the states names are changed. Do you agree? See, the state names are PQRS, PQRS, PQRS. Okay, no problem. First of all, you tell me what will be the final state. First of all, you tell me here what will be the final state. Remember, by default, we create product automata for intersection. Okay, by default, for intersection, we create product automata we create for intersection. So what will be your final state? The final state of this automata will be that state which contains in which both the DFA are in final state. So I can say that will be Z2, Y2. This will be your final state. Okay, is this clear? Your final state will be this state, Z2, Y2. Now see, options are saying that PQRS, the names are given like this: PQRS, PQRS, where P is the initial state in all the options. P is the initial state, R is the final state. So tell me, P is the initial state, R is the final state. Now you let me know what is P here. So P is Z1, P is Z1, Y1, correct? Okay, so remember P is Z1, Y1. This will be your P. P is Z1, Y1. Okay, and what is your R? What is R? R is Z2, Y2. R is Z2, Y2. Okay, so P is Z1, Y1, R is Z2, Y2. Now you create the this Z cross Y. This automata will be like this. These are the symbols A comma B. Okay, the initial state is Z1, Y1. From the initial state, where are we going? On A, where are we going? From this Z1, Y1, where are we going? Please tell me. On symbol A, we are going to Z2, Y1. Okay, we should go to Z2, Y1. We should go to Z2, Y1 or C. And from Z1, Y1 on B, we will go to, or I can say here, I can definitely say R. Can I guarantee there will be R here? Yes or no? And this R is the final state. So now look at this. What I can say, you can see that on B, on B, this must be P. Do you agree that this must be R, this must be P? There is no doubt in this. Do you agree that that here you must have R comma P? So which options are gone? You must have R comma P. So this option is gone. Do you agree? Because this must be R. Definitely this must be R. Yes or no? See, very simple. From P, one thing you can agree with me that that on B we should go to R and here we should go to P. So this is definitely, like, there is no doubt about this. Okay, so now you can see that option B is gone, option C is gone, option D is gone. Only one option is remaining. Only one option is remaining. Only this option is remaining. Yes or no? Only option A is remaining. Now let's fill it. Option A is saying that on A we are going to S. Okay, like see, on A from P, from Z1, Y1, on A we are going to Z2, Y1. So remember, basically Z2, Y1, that is according to option A. You see the option A and tell me what is your Z2, Y1? According to option A, Z2, Y1 is S. Yes or no? Do you agree that according to option A, I am saying according to option A, as per option A, as per option A, this S is your Z2 Y1. Okay. A student is asking, how can I say P is Z1 Y1? Because Z1 Y1 is initial state. In all the options, P is the initial state. In all the options, P is the initial state. So P is Z1 Y1. Is this point clear? A student is asking that why P Z1 Y1? Because see, Z1 Y1 is the initial state in our product automata. And in all the options, P is initial state. So P is Z1 Y1. In all the options, R is final state. And the final state is Z2 Y2. So Z2 Y2 is R. Okay. So now you can see according to option A, S is Z2 Y1. Okay. Z2 Y1 is S. So automatically this is Z1 Y2. What is that? That will be Q. Okay. Yes or no? Now you can just simply fill it. So PQRS. Now you can see where Q will go on A. Q means Z1 Y2. Z1 Y2. On A, it is going to R. Okay. Remember, this is your P. It's like this. Please focus. That basically this is your P. This is your R. Okay. Z1 Y2. Z1 Y2 is your Q. And this is your S. So now easily you can see that where Q is going on A, Q on A to R. Okay. And where Q is going on B, it is going to S. Where R is going on A, R is going on A to Q. Okay. Where S is going on A, S is going on A to P. And S on B, it is going to Q. So your answer should be this. Your answer should be, this is the correct answer. Your answer is SRRS QPPQ. SRRS QPPQ. Okay. SRRS QPPQ. So actually option A is also wrong. Okay. Actually, here there is a typo. Let me tell you. Here this should be PQ. Okay. Is this clear? This should be PQ. This should not be QP. This should be PQ. Okay. If you make it PQ, then this will be correct. So actually, no option is correct for this GATE 2008 question. Actually, no option is correct. No option. But actually, I think that they made a typo in option A. So the best choice, if you have to select one option, then the best choice will be A, because in this A there is a typo. Okay, no option is correct, but there is a typo in option A. Okay, is this clear? So this option A has a typo. So if you have to select one option, then you can select option A. Okay, in the GATE exam, if this type of question comes, let's assume in the future GATE exam, if this type of question comes, then will you leave the options? Will you do that? Will you leave option like no option is correct? Will you leave the question? No, select the best choice. Okay, always select the best choice. Here the best choice is option A. So you should select option A. Actually, let me tell you, this question will definitely become marks to all, because you can challenge this question and it will become marks to all, because no option is correct. So it will become marks to all, but still you should fill the best choice. Okay, whether you fill option A or whether you don't fill option A, you will get marks, because this question will become marks to all. But still, this is a suggestion that you should always select the best possible choice. Okay, so I hope this point is clear. So this question, I hope you understood. Now let's move on. Let's solve this GATE 1998 question. Design a deterministic finite automata using minimum number of states that will recognize the following language: binary strings. When string is interpreted as binary number, ignore the leading zero, then it is divisible by 5. This question we have already done in our lectures, if you remember. Okay, this type of question we have already done in our lectures, so you can check it out. When you basically the decimal value of W is divisible by 5. Okay, this question you can check it out. We have done this type of questions in our lectures. Okay, so thank you everyone. I hope you understood all the questions. Please tell me, did you understand each and every question that we have discussed in this session? Did you understand the complete analysis of each question? Is there any doubt in any question? Let me know. So this is the complete analysis of all the questions based on minimal DFA. Okay. Please check out the pinned comment. Also check out the description. In the description, also in the pinned comment, I have provided all the relevant lectures. Okay, so you can watch those lectures also. Okay. Okay, thank you everyone. So thank you everyone. Please like this session and please share your feedback in the comments. It will motivate us. Okay, thank you.